In the deepest reaches of space, where light has traveled for over 13 billion years to reach us, something impossible lurks in the darkness. We've always believed the early universe was a simpler place, a cosmic nursery where the first stars were just beginning to flicker into existence, where galaxies were mere whispers of what they would become. And yet, the James Webb Space Telescope has just shown us something that shouldn't exist: fully formed, massive galaxies existing when the universe was barely 400 million years old. Galaxies so mature, so impossibly developed, that their very existence threatens to unravel our most fundamental understanding of how everything began. What if everything we thought we knew about the Big Bang was wrong? Join me as we explore the discovery that's sending shockwaves through the scientific community, challenging the very foundation of modern cosmology and potentially rewriting the story of our cosmic origins. Before we dive into this cosmic mystery, I'm curious, where in the world are you watching from right now? And what time is it for you? Are you witnessing this potential revolution in cosmology during your morning coffee, or are you pondering the universe late into the night? Drop your location and time in the comments below. Picture this: you're an archaeologist, and you've just discovered a fully functional smartphone buried beneath the ruins of ancient Rome. Not just any smartphone, a cutting-edge device with features that shouldn't have existed for another 2,000 years. That's essentially what astronomers felt when they first laid eyes on galaxy JDS-GSZ 13-0. This isn't just any galaxy, it's a cosmic impossibility, a celestial artifact that exists 13.4 billion years in the past. And our universe was merely 400 million years old, just 3% of its current age. To put this in perspective, if the universe's entire history were compressed into a single year, we're looking at something that existed in mid-January, when the cosmic calendar had barely begun. But here's where the impossible becomes mind-bending. This galaxy isn't the cosmic equivalent of a primitive stone tool. It's sophisticated, massive, and already churning out stars at a rate that defies everything we thought we understood about the early universe. The galaxy contains roughly 1 billion solar masses worth of stars. Stars that, according to our models, simply shouldn't have had time to form. Dr. Brant Robertson, one of the lead researchers on the discovery team, described the moment of realization as like finding a fully grown oak tree in a field that was planted yesterday. The metaphor is apt, but even it fails to capture the true magnitude of what we're witnessing. This isn't just about one galaxy, it's about dozens of them, all existing in this impossible epoch, all challenging our fundamental understanding of cosmic evolution. The James Webb Space Telescope, with its unprecedented infrared vision, has become our time machine, allowing us to peer deeper into the past than ever before. And what it's showing us is forcing astronomers to confront an uncomfortable truth. The early universe was far more active, far more complex, and far more mysterious than we ever imagined. These galaxies aren't just mature, they're thriving. They show signs of complex chemical evolution, indicating multiple generations of stars have already lived and died. They display organized structures that should have taken billions of years to develop. Most shocking of all, they appear to harbor supermassive black holes at their centers, objects so massive they challenge our understanding of how such giants could have formed so early in cosmic history. The discovery team, led by researchers from the University of Arizona, on working with the JWST, Advanced Deep Extragalactic Survey, initially thought they had made an error. The data seemed too extraordinary to be real. They double-checked their calculations, re-examined their methodology, and consulted with colleagues across the globe. But the evidence remained undeniable. They had discovered galaxies that by all rights should not exist. Time, in the cosmic sense, is everything. It's the fundamental ingredient that allows complexity to emerge from simplicity, order from chaos. The Big Bang Theory gives us a precise recipe. First, you need time for the universe to cool enough for atoms to form. Then, more time for gravity to pull matter together into the first stars. Even more time for those stars to forge heavy elements, dye, and seed space with the building blocks of planets and life. This cosmic recipe has a strict timeline, and JD's GSZ 13-0 and its impossible siblings have just thrown that timeline into chaos. Consider the mathematics of cosmic evolution. The first stars, population 3 stars, were supposed to be massive, short-lived giants that burned bright and died young, perhaps within a few million years. Their deaths would seed the universe with heavier elements, allowing the next generation of stars to form. This process should repeat several times before you get the diverse stellar populations we see in mature galaxies. But here's the problem. Even if everything happened at breakneck speed, there simply wasn't enough time. 400 million years sounds like an eternity to us, but in cosmic terms, it's barely a blink. It's like trying to cook a 5-course meal in the time it takes to boil water. The numbers tell a stark story. For these galaxies to exist with their observed stellar masses, star formation would have had to proceed at rates that exceed even our most optimistic models. We're talking about stellar nurseries that were producing new stars at rates hundreds of times faster than anything we observe in the modern universe. Dr. Emma Curtis Lake, another member of the Discovery team, puts it in perspective. It's as if we discovered a city with skyscrapers, universities, and complex infrastructure on a continent that was supposed to still be underwater. The analogy captures the essential impossibility, not just of the timeline, but of the level of organization and complexity these early galaxies display. The implications ripple outward like shockwaves. If these galaxies are real, and every piece of evidence suggests they are, then our understanding of the early universe is fundamentally flawed. The period we call the Dark Ages, when the universe was supposedly a quiet place of slowly forming structures, was anything but dark. It was a time of furious activity, rapid evolution, and cosmic construction on a scale we never imagined possible. The announcement of these discoveries didn't just raise eyebrows in the astronomical community. It triggered what some scientists are calling the biggest challenge to cosmological orthodoxy since the discovery of dark energy. Conference rooms that typically buzz with polite academic discourse erupted into heated debates. Peer review processes that usually take months were expedited as scientists rushed to either confirm or debunk these extraordinary claims. Dr. Rohan Naidu from the Harvard-Smithsonian Center for Astrophysics captured the mood perfectly. It's like being told that everything you thought you knew about growing up was wrong, that babies can actually run marathons and solve calculus problems. The discovery has created what philosophers of science call a paradigm crisis, a moment when the fundamental assumptions of a field are called into question. The scientific method, however, is designed for exactly these moments. Rather than dismiss the unexpected, researchers have mobilized on an unprecedented scale. International collaborations have formed overnight. Theoretical physicists are working around the clock to develop new models. Observational teams are requesting emergency time on the world's most powerful telescopes to gather additional data. But the shockwave extends far beyond astronomy. Cosmology sits at the intersection of physics, philosophy, and human understanding. When we challenge the Big Bang model, we're not just questioning a scientific theory, we're potentially rewriting humanity's origin story. The Big Bang theory isn't merely a description of cosmic events. It's the scientific foundation for how we understand our place in the universe. Cosmology sits at the intersection of physics, philosophy, and human understanding. The controversy has even reached the public sphere. Social media platforms buzz with discussions about whether scientists got it wrong. Science communicators find themselves in the difficult position of explaining that this isn't a failure of science, but rather science working exactly as it should, constantly testing, refining, and when necessary, revolutionizing our understanding of reality. Within the scientific community, camps are forming. Conservative cosmologists argue for caution, suggesting that measurement errors or unknown systematic effects might explain the anomalous observations. They point to the complexity of measuring distances and ages in the early universe, where the usual cosmic signposts become unreliable. Progressive voices, meanwhile, argue that the evidence is too strong to ignore, and that clinging to outdated models in the face of revolutionary data is intellectually dishonest. They point to the consistency of the observations across multiple independent teams and the robustness of the JWST data. Perhaps most intriguingly, a third camp is emerging. Scientists who see this as an opportunity for a fundamental breakthrough. Catherine Fries, from the University of Texas at Austin, represents this perspective. These discoveries might be telling us something profound about the nature of dark matter, dark energy, or even the fundamental structure of space-time itself. Rather than seeing this as a crisis, we should see it as the universe offering us a gift, a chance to understand reality at a deeper level. The implications for future research are staggering. Funding agencies are redirecting resources toward early universe studies. Graduate students are pivoting their dissertations toward these new frontiers. Entire research programs built around standard cosmological models are being reconsidered. Most significantly, this discovery is changing how we approach scientific truth itself. The early universe, once considered a well-understood chapter in cosmic history, has suddenly become the most mysterious and exciting frontier in astronomy. We're witnessing what Thomas Kuhn called a scientific revolution, a moment when the fundamental structure of scientific understanding shifts beneath our feet. The reverberations will likely continue for decades. Like the discovery of cosmic expansion that led to the Big Bang theory itself, or the detection of cosmic microwave background radiation that confirmed it, these JWST observations may mark the beginning of an entirely new chapter in our understanding of the universe. We stand at the threshold of what could be the most significant revision to cosmology since Einstein first proposed that space-time itself could be curved. To understand why these JWST discoveries are so revolutionary, we need to journey back to the beginning, not just of our universe, but of our understanding of how everything came to be. The Big Bang theory isn't just a scientific model. It's humanity's most successful attempt to answer the ultimate question, how did everything begin? The story starts in 1929 with Edwin Hubble's groundbreaking observation that distant galaxies were moving away from us, and the farther they were, the faster they receded. This wasn't just motion through space, it was the expansion of space itself. Imagine dots on a balloon being inflated. Each dot sees all others moving away, with the most distant ones appearing to retreat fastest. Hubble had discovered that our universe was growing. If the universe is expanding now, then logically, it must have been smaller in the past. Follow this reasoning backward far enough, and you arrive at a singular moment, roughly 13.8 billion years ago, when all of space, time, matter, and energy emerged from an infinitesimally small point. This wasn't an explosion in space. It was the explosion of space itself. The Big Bang theory, refined over decades by brilliant minds like George Gamow, Ralph Alpher, and Robert Herman, paints a precise picture of cosmic evolution. In the first fraction of a second, the universe underwent a period of exponential expansion called inflation, smoothing out irregularities and setting the stage for structure formation. As the universe cooled, it underwent a series of phase transitions, first allowing the fundamental forces to separate, then enabling the formation of the first atomic nuclei, and finally, about 380,000 years later, becoming cool enough for electrons to bind with protons, forming the first atoms. This moment, called recombination, was crucial. For the first time, the universe became transparent to light. The cosmic microwave background radiation we detect today is the afterglow of this cosmic dawn, a baby picture of the universe that has provided our most detailed evidence for Big Bang cosmology. But here's where the timeline becomes critical for our story. After recombination came the period cosmologists call the Dark Ages, a time when the universe was filled with neutral hydrogen and helium, but no stars had yet formed to light up the cosmos. According to standard models, this dark period lasted several 100 million years, with the first stars finally igniting around 200–400 million years after the Big Bang. These first stars, dubbed population 3 stars, were supposed to be massive, metal-free giants that burned bright and died young. Their spectacular deaths as supernovae would have seeded the universe with heavier elements, the carbon, oxygen, and iron that make planets and life possible. Only after several generations of stellar death and rebirth could complex structures like mature galaxies begin to form. This timeline wasn't arbitrary, it was based on fundamental physics. The process of gravitational collapse, nuclear fusion, and chemical enrichment simply takes time. Even in the most optimistic scenarios, building a mature galaxy with billions of stars and complex structures should require at least 1 billion years, possibly more. The mathematics of structure formation supports this timeline. Small quantum fluctuations in the early universe, amplified by cosmic expansion, provided the seeds for all later structure. But these seeds were tiny variations in density of only 1 part in 100,000. Dufourier's seeds were tiny variations in density of only 1 part in 100,000. Gravity, while inexorable, is also relatively weak. Building massive structures from such small beginnings is like constructing a cathedral 1 grain of sand at a time. Furthermore, the physics of star formation itself imposes limits. The first stars had to form from primordial gas, with no heavy elements to help cool the material and enable fragmentation into smaller, more numerous stars. This meant early star formation was inefficient, producing mostly massive stars that lived fast and died young. The Big Bang model also made specific predictions about what we should see when we look deep into space and far back in time. We should see a gradual increase in cosmic complexity, simple structures giving way to more elaborate ones as the universe ages. The most distant galaxies should be smaller, less massive, and more chaotic than their modern counterparts. For decades, every observation confirmed this gradual evolution. The Phasey and Neve Space Telescope showed us exactly what we expected: distant galaxies that appeared younger, smaller, and less organized than nearby ones. The cosmic story seemed complete, elegant, and confirmed by observation. This wasn't just scientific theory. It was a creation myth backed by mathematics, observation, and the most sophisticated understanding of physics humanity had ever achieved. The Big Bang model successfully predicted the abundance of light elements, the temperature and properties of the cosmic microwave background, and the large-scale structure of the universe. It was, by any measure, one of science's greatest triumphs. But science's greatest strength is also its defining characteristic. It remains open to revision when new evidence emerges. And the James Webb Space Telescope has just provided evidence that challenges not just the details of cosmic evolution, but its fundamental timeline. The universe, it seems, was far more precocious than we ever imagined. The period between 400,000 and 400 million years after the Big Bang has always held a special place in cosmology. We called it the Dark Ages because, quite literally, there were no sources of light in the universe. The cosmic microwave background had faded to infrared wavelengths, and the first stars hadn't yet formed. It was supposed to be a quiet time, a cosmic intermission between the drama of the Big Bang and the spectacular light show that would follow with the first stellar ignition. This wasn't just poetic language. The darkness was real and profound. Without stars or galaxies, the universe was filled only with cooling gas, primarily hydrogen and helium, slowly coalescing under gravity's patient pull. Computer simulations showed how tiny density fluctuations would gradually grow, forming the scaffolding upon which the first structures would eventually build. It was cosmic construction in slow motion, governed by the gentle mathematics of gravitational collapse. The narrative was compelling and seemed ironclad. After all, you can't light a fire without fuel, and you can't build complex structures without time. The Dark Ages were dark by necessity, a required period of patient assembly before the universe could become the brilliant, complex cosmos we observe today. But JWST's observations suggest this narrative was fundamentally wrong. Rather than a quiet period of gradual assembly, the Dark Ages appear to have been a time of furious activity. These impossibly mature galaxies didn't slowly coalesce over billions of years. They seemed to spring into existence with shocking rapidity. Dr. Garth Illingworth, from UC Santa Cruz, who has spent decades studying galaxy formation, describes the revelation. It's like thinking a forest grows slowly over centuries, only to discover that some forests can apparently grow to full maturity in a matter of months. Everything we thought we knew about the pace of cosmic evolution has been turned upside down. The implications cascade through our understanding of cosmic history, If massive, mature galaxies existed just 400 million years after the Big Bang, then star formation, chemical enrichment, and structural assembly must have proceeded at rates that challenge our most fundamental assumptions about astrophysics. Consider what this means for stellar evolution. These early galaxies show spectroscopic evidence of multiple stellar populations, different generations of stars with varying chemical compositions. This suggests that not only did the first stars form rapidly, but they also lived, died, and enriched their environments with heavy elements in timeframes we previously considered impossible. The discovery also forces us to reconsider the role of dark matter in early structure formation. Dark matter, which makes up roughly 85% of all matter in the universe, was supposed to provide the gravitational framework upon which normal matter could build structures. But if structures formed much more rapidly than expected, perhaps our understanding of dark matter's behavior in the early universe is incomplete. Some researchers are exploring whether dark matter might have had different properties in the early universe. Perhaps it was more strongly interacting, allowing for faster structure formation. Others wonder if our models of how normal matter responds to dark matter's gravitational influence need revision. The revised timeline also affects our understanding of cosmic regionization, the period when the first stars and galaxies produced enough ultraviolet light to ionize the hydrogen throughout the universe, ending the Dark Ages. If large, mature galaxies existed earlier than expected, regionization might have begun sooner and proceeded differently than our models predict. But perhaps most profoundly, these discoveries suggest that the early universe was a far more dynamic and active place than we ever imagined. Instead of a quiet cosmic nursery, we're seeing evidence of a period of intense creativity, where the fundamental processes of cosmic evolution operated in overdrive. The psychological impact on astronomers has been significant. Many researchers built their careers on models of gradual cosmic evolution. Suddenly, they're confronting evidence that the universe was capable of rapid, almost explosive development that challenges decades of theoretical work. Yet, there's also excitement. Science thrives on surprises, and these discoveries open entirely new avenues of research. Understanding how the universe could evolve so rapidly might reveal new physics, new insights into the nature of dark matter and dark energy, or even new principles governing structure formation that we haven't yet discovered. The Big Bang theory wasn't just successful, it was perhaps too successful. For decades, it explained every major observation about the universe with elegant precision. The cosmic microwave background matched predictions to remarkable accuracy. The abundance of light elements aligned perfectly with theoretical calculations. The large-scale structure of the universe emerged exactly as computer simulations predicted. This success bred confidence, perhaps even complacency. The standard model of cosmology, built around Big Bang theory, became so well established that questioning its fundamental assumptions seemed almost heretical. Graduate students learned it as settled science. Textbooks presented it as established fact. The universe's story appeared complete. But science has a way of humbling even its most successful theories. These JWST discoveries represent what philosophers of science call anomalous data, observations that don't fit within the existing paradigm. History shows us that such anomalies are often harbingers of revolutionary change. Consider the historical parallels. In the early 20th century, classical physics seemed complete until a few puzzling observations: blackbody radiation, the photoelectric effect, the stability of atoms, led to the quantum revolution. Similarly, Newton's laws worked perfectly until precise observations of Mercury's orbit revealed discrepancies that ultimately led to Einstein's theory of relativity. The current crisis in cosmology follows a similar pattern. The Big Bang theory's predictions about early galaxy formation were specific and seemingly well-founded. The timeline of cosmic evolution was based on fundamental physics, the rates of nuclear fusion, stellar evolution, and gravitational collapse. These weren't wild guesses, but carefully calculated predictions based on well-tested physical principles. Yet here we are, confronted with galaxies that appear to violate these carefully constructed timelines. The anomaly is too significant to ignore, and too consistent across multiple observations to dismiss as measurement error. Dr. Joel Primack, a theoretical cosmologist at UC Santa Cruz, captures the moment we're experiencing what it must have felt like to be a physicist in 1900, when everything seemed understood. Few inconvenient facts changed everything. These galaxies are our inconvenient facts. The seeds of doubt are spreading beyond just galaxy formation. If our models are wrong about early cosmic evolution, what else might they be wrong about? The discovery is prompting researchers to re-examine other aspects of Big Bang cosmology, from the nature of dark matter to the mechanism of cosmic inflation. Some scientists worry that we've become too attached to elegant mathematical models and haven't remained sufficiently open to observational surprises. The universe, after all, is under no obligation to conform to our theories, no matter how beautiful or well-reasoned they might be. Others argue that this crisis represents science at its best, constantly testing, refining, and when necessary, revolutionizing our understanding. The willingness to question even our most successful theories when confronted with new evidence is what separates science from dogma. The implications extend beyond astronomy. If the Big Bang theory requires major revisions, it could affect our understanding of fundamental physics, the nature of space and time, and even philosophical questions about the origin and destiny of the universe. Perhaps most intriguingly, these discoveries remind us that the universe still holds profound mysteries. Despite centuries of scientific progress, despite our sophisticated instruments and elegant theories, the cosmos can still surprise us. In an age when some proclaimed that physics was nearly complete, these impossible galaxies serve as a humbling reminder that we've only just begun to understand the universe we inhabit. The James Webb Space Telescope isn't just humanity's most powerful eye on the universe. It's a time machine that has fundamentally changed our relationship with cosmic history. When we look at distant galaxies, we're not seeing them as they are today, but as they were billions of years ago when their light first began its journey to us. JWST has pushed this temporal voyeurism to unprecedented extremes, allowing us to witness the universe when it was barely a toddler. Understanding why JWST can see these impossible galaxies requires understanding the nature of cosmic expansion itself. As the universe expands, it stretches the wavelengths of light, traveling through space. Light that left distant galaxies as visible wavelengths arrives at Earth dramatically redshifted into the infrared spectrum. The more distant the galaxy, the more extreme this redshift becomes. This is where JWST's revolutionary design becomes crucial. Unlike the Hubble Space Telescope, which primarily observes invisible light, JWST was built specifically to capture infrared radiation. Its massive 6.5-meter segmented mirror collects light with unprecedented sensitivity, while its instruments are cooled to just 7 degrees above absolute zero to minimize thermal interference. The technological achievement this represents cannot be overstated. Each of JWST's 18 hexagonal mirror segments had to be positioned with nanometer precision, accuracy equivalent to placing a dime on top of the Washington Monument in DC and hitting it with a laser beam from New York City. The telescope's sunshield, roughly the size of a tennis court, had to deploy perfectly in the vacuum of space, protecting the instruments from the sun's heat while maintaining their frigid operating temperatures. But the real magic lies in JWST's infrared instruments. The near-infrared camera, NIRCam, can detect light that's been redshifted by factors of 10 or more, meaning it can observe galaxies whose light has been traveling for over 13 billion years. The mid-infrared instrument, MIRI, pushes even deeper into the infrared spectrum, revealing details about these ancient galaxies that were completely invisible to previous telescopes. Dr. Marcia Rique, principal investigator for NICAM, explains the breakthrough. It's like having been colorblind your entire life and suddenly seeing the full spectrum. We're not just seeing farther, we're seeing things that were literally invisible before. The spacecraft's position at the second Lagrange point, 1.5 million kilometers from Earth, provides the perfect vantage point for these observations. Here, JWST orbits the Sun in sync with Earth, maintaining a stable thermal environment while avoiding the planet's infrared glow that would interfere with sensitive observations. The spacecraft's position at the second Lagrange point, 1.5 million kilometers from Earth, provides the perfect vantage point for these observations. When JWST first captured images of galaxy JDIS GS-Z 13-0 and its impossible companions, the data initially seemed too extraordinary to believe. These galaxies appeared bright and structured in ways that contradicted every prediction about what the early universe should look like. The temptation to dismiss the observations as instrumental artifacts was strong, but repeated observations and careful calibration confirmed their reality. The telescope's spectroscopic capabilities add another dimension to these discoveries. By spreading the light from these ancient galaxies into their component wavelengths, JWST can determine not just their distances and ages, but also their chemical compositions, star formation rates, and internal dynamics. It's like performing a detailed medical examination on a patient from 13 billion years ago. Perhaps most remarkably, JWST can observe multiple epochs of cosmic history simultaneously. In a single deep field image, the telescope captures galaxies from various cosmic ages, some from when the universe was 13 billion years old, others from when it was only 400 million years old. It's as if we could look at a single photograph and see both modern skyscrapers and ancient cave paintings side by side. The engineering triumph that made these discoveries possible took decades to achieve. JWST's development began in the 1990s, survived multiple redesigns and budget crises, and finally launched on Christmas Day 2021. The 6-month commissioning period that followed was perhaps the most nerve-wracking time in astronomical history, as engineers carefully deployed and calibrated each component of this incredibly complex machine. Now, less than 2 years into its mission, JWST has already revolutionized our understanding of the early universe. Every observation session yields new surprises, new challenges to established theory, new glimpses into cosmic epochs that were previously beyond our reach. The telescope's impact extends beyond individual discoveries. It has democratized deep field astronomy, making observations that once required months of Hubble time accessible in hours. Graduate students can now study the early universe with a precision that was unimaginable just a few years ago. But perhaps JWST's greatest achievement is philosophical. It has reminded us that the universe is far stranger, more complex, and more wonderful than our models suggest. In an age of increasing certainty about cosmic evolution, these impossible galaxies serve as a humbling reminder that the universe still holds profound secrets waiting to be discovered. Light is the universe's historian, carrying within its wavelengths the story of everything it has encountered on its cosmic journey. When astronomers analyze the light from these impossibly ancient galaxies, they're not just taking pretty pictures. They're performing archaeology on a cosmic scale, extracting information from photons that have been traveling through space since the universe was in its infancy. The process begins with understanding redshift, one of astronomy's most powerful tools for measuring cosmic distances and ages. As the universe expands, it stretches the wavelengths of light traveling through space. Imagine a wave on a stretching rubber sheet. As the sheet expands, the wave becomes longer and longer. Similarly, light from distant galaxies gets stretched to longer, redder wavelengths during its journey to Earth. The amount of redshift tells us how much the universe has expanded since the light began its journey, which directly translates to the galaxy's distance and the time the light has been traveling. Galaxy JD's JSZ 13-0, for example, has a redshift of 13, meaning the universe has expanded by a factor of 14 since its light began the journey to us. This corresponds to looking back over 13.4 billion years in time. But redshift is just the beginning. JWST's spectroscopic instruments break this ancient light into its component wavelengths, creating what astronomers call a spectrum, essentially a fingerprint that reveals the galaxy's physical properties. Different chemical elements absorb and emit light at specific wavelengths, creating characteristic patterns that remain identifiable even after billions of years of cosmic expansion. When astronomers examine the spectrum of these early galaxies, They can identify the signatures of various elements: hydrogen, helium, oxygen, carbon, and iron. The relative abundances of these elements tell a story of stellar evolution and chemical enrichment. The presence of heavy elements indicates that multiple generations of stars have already lived and died, forging these elements in their nuclear furnaces and dispersing them through supernova explosions. The brightness and color of the light reveal the galaxy's stellar population, how many stars it contains, how rapidly they're forming, and what stage of evolution they're in. Young, hot stars emit blue light, while older, cooler stars appear redder. The overall spectrum allows astronomers to determine the galaxy's age, mass, and star formation history with remarkable precision. Dr. Daniel Eisenstein from the Harvard-Smithsonian Center for Astrophysics describes the process. It's like being a detective, examining evidence from a crime scene that's 13 billion years old. Every wavelength of light carries clues about what happened in that galaxy and when it happened. The Doppler effect provides additional information about the galaxy's internal dynamics. Just as a siren's pitch changes as an ambulance approaches and recedes, light from different parts of a rotating galaxy will be slightly blue-shifted or red-shifted, depending on whether that region is moving toward or away from us. This allows astronomers to measure the galaxy's rotation speed and estimate its total mass, including the invisible dark matter that dominates its gravitational field. JWST's unprecedented sensitivity allows it to detect spectral features that were previously impossible to observe in such distant galaxies. Lines from ionized oxygen, neon, and other elements provide information about the galaxy's star formation rate and the intensity of the radiation field within it. These observations are crucial for understanding how these early galaxies could have formed so rapidly. The telescope can even detect the signatures of supermassive black holes at the centers of these ancient galaxies. The intense radiation from matter falling into these black holes creates characteristic spectral features that stand out against the light from surrounding stars. Finding such massive black holes in galaxies from the early universe adds another layer to the impossibility of these objects. Perhaps most remarkably, JWST can observe the same galaxy at different stages of cosmic history by looking at light that left at different times. Gravitational lensing by intervening galaxy clusters can magnify and distort the images of background galaxies, sometimes creating multiple images that show the same object at different epochs. It's like having a cosmic time-lapse movie of galaxy evolution. This ancient light archaeology is revealing that the early universe was far more complex and active than we ever imagined, setting the stage for a fundamental revision of our understanding of cosmic evolution. The numbers emerging from JWST's observations aren't just surprising, like the scientifically shocking. When the first measurements of galaxy JD's GSZ 13-0 were processed, researchers initially assumed they had made an error. The galaxy appeared to contain roughly 1 billion solar masses worth of stars, organized into a structured disk with clear evidence of rotation and chemical evolution. For a galaxy existing just 400 million years after the Big Bang, these properties were supposed to be impossible. To appreciate the magnitude of this impossibility, consider the mathematics of stellar evolution. Stars don't form instantly, even under the most optimal conditions. The process of gravitational collapse, nuclear ignition, and stellar maturation takes millions of years. For massive stars that burn bright and die young, the entire life cycle from birth to supernova death spans perhaps 10⁻20 million years. Lower mass stars like our Sun require billions of years to evolve significantly. Yet these JWST observations suggest that not only did the first stars form rapidly, but they also lived, died, and enriched their environments with heavy elements on timescales that challenge our fundamental understanding of stellar physics. The spectroscopic data shows clear evidence of carbon, oxygen, and even iron in these early galaxies, elements that can only be forged in stellar cores and distributed through supernova explosions. Dr. Roberto Maiolino from Cambridge University, who led much of the spectroscopic analysis, describes the revelation. We're seeing chemical enrichment patterns that should represent the end result of several generations of stellar evolution, compressed into what appears to be just a few 100 million years. It's as if we discovered a 20-year-old person with the accumulated wisdom and experience of someone who had lived for centuries. The structural properties of these galaxies add another layer of impossibility. Modern spiral galaxies, like our Milky Way, develop their organized disk structures over billions of years through a complex process of mergers, accretion, and gravitational settling. The fact that some of these early galaxies already display organized rotation patterns and disk-like structures suggests that galaxy assembly proceeded far more rapidly than any theoretical model predicted. Order. The mass measurements are equally problematic. Our galaxy formation theory predicts that early galaxies should be relatively small, perhaps containing millions of stars rather than billions. The massive stellar populations observed in these JWST targets require prodigious rates of star formation that exceed anything observed in the modern universe. We're talking about stellar nurseries that were producing new stars at rates hundreds or even thousands of times faster than the most active star-forming regions we observe today. But perhaps the most shocking discovery involves the supermassive black holes apparently residing at the centers of these ancient galaxies. The active galactic nucleus, AGN signatures, detected in several of these early systems indicate the presence of black holes with masses ranging from millions to billions of times that of our Sun. The formation of such massive black holes in the early universe presents what cosmologists call the impossible early quasar problem. Standard black hole formation theory suggests that stellar mass black holes, perhaps 10⁻100 times the mass of the Sun, form from the collapse of massive stars. These seed black holes then grow by accreting surrounding material, but this growth process has fundamental limits. The Eddington limit describes the maximum rate at which a black hole can accrete matter before the outward pressure of radiation balances the inward pull of gravity. Even assuming continuous accretion at the Eddington limit, growing a stellar mass black hole to supermassive proportions requires hundreds of millions to billions of years. Yet here, we have apparent evidence of supermassive black holes existing when the universe was only 400 million years old. Barely enough time for the first stars to form, let alone for their remnant black holes to grow to such enormous sizes. The Discovery team, led by Dr. Kevin Hanline from the University of Arizona, initially questioned their own measurements. We ran the data analysis multiple times, checked for systematic errors, and consulted with independent teams. Hanline explains, every analysis confirmed what we were seeing, even though what we were seeing seemed to violate fundamental principles of astrophysics. The consistency of these observations across multiple independent surveys makes measurement error unlikely. The JWST Advanced Deep Extragalactic Survey, JD's team, the Sears collaboration, and several other research groups have all identified similar populations of impossibly mature early galaxies. The data comes from different instruments, different observing strategies, and different analysis techniques, yet the conclusions remain remarkably consistent. The statistical significance of these discoveries is overwhelming. We're not talking about one or two anomalous objects that might represent unusual circumstances. Dozens of these impossibly mature galaxies have been identified, suggesting that rapid evolution was the norm rather than the exception in the early universe. The implications for our understanding of cosmic evolution are staggering. If galaxies could form and evolve this rapidly in the early universe, it suggests that either our models of structure formation are fundamentally flawed, or that physical processes operated differently when the universe was young. Some researchers are exploring whether the laws of physics themselves might have been different in the early universe, or whether we're missing crucial components in our understanding of dark matter and dark energy. The data also raises profound questions about the nature of the first generation of stars. Population 3 stars were supposed to be massive, metal-free giants that lived fast and died young. But the rapid chemical enrichment observed in these early galaxies suggests that stellar evolution and nucleosynthesis proceeded far more efficiently than our models predict. The data also raises profound questions about the nature of the first generation of stars. Population 3 stars were supposed to be massive, metal-free giants that lived fars. As more data pours in from JWST's ongoing observations, the picture becomes increasingly clear. The early universe was a far more dynamic, active, and rapidly evolving place than we ever imagined. These aren't just minor corrections to our models. They represent a fundamental challenge to our understanding of how cosmic structure emerged from the primordial smoothness of the early universe. The scientific community is still grappling with the implications of these discoveries. Theoretical astrophysicists are working frantically to develop new models that can explain rapid galaxy formation. Observational teams are requesting additional telescope time to study even more distant galaxies. The field of cosmology is experiencing what can only be described as a revolution in understanding driven by data that refuses to conform to our expectations. Galaxy formation was supposed to be a story of patience, a cosmic construction project spanning billions of years, governed by the slow, steady accumulation of matter under gravity's gentle influence. The Standard Model, refined over decades of research, painted a picture of gradual assembly, tiny fluctuations in the cosmic microwave background, serving as seeds, dark matter providing the scaffolding, and ordinary matter slowly condensing into the first stars and proto-galaxies. This wasn't speculation. It was based on some of the most successful theories in all of physics. The Lambda CDM model, Lambda Cold Dark Matter, described how quantum fluctuations in the early universe, inflated to cosmic scales during the period of cosmic inflation, would grow under gravitational influence. Computer simulations based on these principles successfully reproduced the large-scale structure of the universe we observe today, from the cosmic web of galaxy filaments to the clustering patterns of galaxy groups. The theoretical framework was elegant and compelling. Dark matter, comprising roughly 85% of all matter in the universe, would collapse into halos, gravitational wells that would eventually trap ordinary matter. Within these dark matter halos, gas would cool and condense, eventually reaching densities sufficient for star formation. The first stars would be massive, short-lived giants that would enrich their surroundings with heavy elements when they died as supernovae. This process was expected to be hierarchical, with smaller structures forming first and then merging to create progressively larger ones. Tiny proto-galaxies, containing perhaps millions of stars, would collide and merge over hundreds of millions of years, eventually building the massive spiral and elliptical galaxies we see in the modern universe. It was cosmic construction through merger and acquisition, a universe-sized version of corporate consolidation. The mathematics of this process seemed ironclad. Gravitational collapse follows well-understood physics. Einstein's equations of general relativity describe how matter curves space-time, while the dynamics of gas cooling and star formation can be modeled using principles of thermodynamics and nuclear physics. When cosmologists ran sophisticated computer simulations incorporating these physical processes, they consistently predicted that large, mature galaxies shouldn't exist until at least 1 billion years after the Big Bang. Dr. Volker Springel, whose Millennium simulation became the gold standard for modeling cosmic structure formation, explains the theoretical foundation. Galaxy formation is fundamentally limited by physics. Inevitability is fundamentally limited by physics. You can't make stars faster than nuclear fusion allows. You can't cool gas faster than thermodynamics permits. And you can't build massive structures faster than gravity can pull matter together. These are fundamental constraints that any theory of galaxy formation must respect. The observational evidence seemed to support this gradual formation scenario perfectly. The Hubble Space Telescope's deep field observations showed exactly what the models predicted. Distant galaxies that appeared smaller, more irregular, and less massive than their modern counterparts. The famous Hubble Ultra Deep Field revealed a universe where ancient galaxies looked like cosmic teenagers, awkward, still growing, not yet settled into the mature forms we see nearby. The chemical evolution of galaxies also supported the Standard Model. Modern galaxies show a clear relationship between their age and their heavy element content. Older galaxies have had more time for successive generations of stars to forge and distribute elements like carbon, oxygen, and iron. This metallicity gradient provided strong evidence for the gradual enrichment process predicted by standard galaxy formation theory. But the JWST discoveries have shattered this comfortable picture hard. The galaxies we're observing at redshift 10^-13, corresponding to when the universe was only 400-600 million years old, don't look like cosmic teenagers. They look like fully mature systems with all the complexity and organization we associate with galaxies that have had billions of years to evolve. These early galaxies display several characteristics that shouldn't exist according to our models. First, they're far too massive, containing billions of stars worth of material. Second, they show evidence of organized structure, rotation patterns, and disk-like morphologies that should take eons to develop. Third, they exhibit complex chemical compositions, indicating multiple generations of stellar evolution. Fourth, many appear to harbor supermassive black holes that would require hundreds of millions of years to grow from stellar remnants. The paradox deepens when we consider the efficiency required to build such systems so rapidly. Or galaxy formation is typically a very inefficient process. Most of the matter in the universe remains in the form of hot diffuse gas that never collapses into stars. Only about 5 to 10% of the available matter typically ends up in stellar form, even in the most efficient modern galaxies. Yet these early systems appear to have converted matter into stars with unprecedented efficiency. The stellar masses observed in these JWST galaxies require that 20 to 30% or more of the available matter was converted into stars within the first few 100 million years of cosmic history. This level of efficiency exceeds anything observed in the modern universe and challenges our understanding of the physical processes that regulate star formation. The timing problem becomes even more acute when we consider that galaxy formation isn't just about making stars, it's about organizing them into coherent structures. Modern galaxies exhibit complex internal dynamics, with spiral arms, stellar halos, and well-defined rotation curves that reflect billions of years of gravitational evolution. The fact that some of these early galaxies already display organized rotation patterns suggests that the process of dynamical relaxation, the settling of stellar orbits into stable configurations, occurred far more rapidly than physics should allow. Dr. Sandra Faber, from UC Santa Cruz, whose pioneering work on galaxy evolution spans 4 decades, captures the magnitude of the challenge. It's as if we discovered fully grown redwood trees in a forest that was planted last week. The physics simply doesn't add up. We're being forced to question fundamental assumptions about how cosmic structure forms. The implications extend beyond just galaxy formation to our understanding of the early universe as a whole. If massive structures could form so rapidly, it suggests that the early universe was either far denser than we thought, operated under different physical laws, or contained unknown components that accelerated structure formation in ways we don't yet understand. Time, in the cosmic sense, is the most precious resource in the universe. Every physical process, from nuclear fusion in stellar cores to the gradual settling of stellar orbits in galactic disks, requires specific amounts of time to complete. The JWST discoveries have revealed galaxies that appear to have accomplished billions of years' worth of evolution in just a few 100 million years, creating what cosmologists are calling the missing time problem. To understand the severity of this temporal impossibility, consider the life cycle of stars themselves. Whole, the most massive stars, which burn through their nuclear fuel most rapidly, still require at least 3-5 million years to evolve from their initial collapse to their final supernova explosion. Lower mass stars like our Sun need billions of years to evolve significantly. Yet the chemical compositions observed in these early galaxies suggest that multiple generations of both massive and intermediate mass stars have already completed their life cycles. The mathematics is unforgiving. If we assume the first stars formed immediately, when the universe was 200 million years old, itself an optimistic assumption, there would only be 200 million years available for stellar evolution. Before we observe these mature galaxies, at 400 million years after the Big Bang. This time frame might allow for one, perhaps two generations of massive stars to live and die, but the heavy element abundances observed suggest far more extensive chemical evolution. Dr. Anna Friebel from MIT, an expert on stellar archaeology and chemical evolution, puts the problem in perspective. We're seeing iron abundances in these early galaxies that typically require 10-15 generations of stellar evolution to produce. It's like finding a fine wine that claims to be aged for centuries, but was bottled last month. The chemistry doesn't match the timeline. The structural evolution of galaxies presents an equally severe timing problem. Modern galaxies achieve their organized forms through a process called dynamical relaxation, where gravitational interactions gradually settle stellar orbits into stable, predictable patterns. This process operates on what astronomers call the dynamical timescale, typically hundreds of millions to billions of years for galaxy-sized systems. Yet some of these early JWST galaxies already display the organized rotation patterns and disk-like structures that should require multiple dynamical timescales to develop. It's as if we discovered a perfectly choreographed ballet performance by dancers who had only been practicing for a few days. The supermassive black hole problem adds yet another layer to the temporal paradox. Even under the most optimistic assumptions about black hole growth, building a billion solar mass black hole from a stellar remnant requires continuous feeding at near maximum rates for at least 400–500 million years. The supermassive black hole problem adds yet another layer to the temporal paradox. But some of these early galaxies appear to host such massive black holes when the universe was only 400 million years old, leaving virtually no time for the growth process to occur. Theoretical astrophysicist Dr. Priyamvada Natarajan from Yale University describes the challenge. We're essentially trying to explain how you can bake a cake before you've had time to mix the ingredients. The physics of black hole accretion has fundamental speed limits that these observations seem to violate. The missing time problem forces us to confront uncomfortable possibilities about our understanding of the early universe. Either physical processes operated far more rapidly than we thought possible, or our models of cosmic chronology are fundamentally flawed. Some researchers are exploring whether the early universe had different physical properties that allowed for accelerated evolution. One intriguing possibility involves the density of the early universe. While the universe as a whole was denser in the past, the local density within collapsing structures might have been orders of magnitude higher than our models predict. Higher densities could accelerate star formation, speed up stellar evolution, and enable more rapid black hole growth. But achieving the required density enhancements would require initial conditions far more extreme than anything predicted by standard inflation models. Another possibility involves the efficiency of early star formation. If the first stars formed in much larger numbers and with different mass distributions than we assumed, it might be possible to accelerate chemical evolution and structure formation. However, this would require abandoning well-established theories about population 3 stellar formation and initial mass functions, initial mass functions. Some researchers are even questioning whether our understanding of stellar evolution timescales is complete. Perhaps massive stars in the early universe, forming in environments with different metallicities and densities, evolved more rapidly than their modern counterparts. But such changes would require revisions to fundamental stellar physics that have been tested extensively in laboratory and observational settings. The missing time problem also raises questions about our measurement techniques. Could systematic errors in distance determinations or age estimates explain these temporal paradoxes? Multiple independent teams have carefully checked their methodologies, and the consistency of results across different observational approaches makes measurement error an unlikely explanation. Perhaps most troubling, the missing time problem isn't isolated to just a few anomalous objects. The JWST surveys are revealing substantial populations of these impossibly mature early galaxies, suggesting that rapid evolution was common rather than exceptional in the early universe. As Dr. Casey Papovich from Texas A&M University observes, We're not just missing a little bit of time, we're missing most of the time these processes should require. It's forcing us to reconsider whether our understanding of time itself in the early universe might be incomplete. Science's greatest moments often occur when carefully constructed theories collide with stubborn observational facts. The JWST discoveries represent exactly such a collision, a moment when the universe refuses to conform to our most sophisticated models, forcing us to confront the possibility that reality is stranger than our theories suggest. The conflict isn't subtle or ambiguous. Our best models of galaxy formation, based on well-tested physics and confirmed by decades of observations, make specific, quantitative predictions about what the early universe should look like. These predictions aren't vague generalities, but precise mathematical statements about galaxy masses, chemical compositions, and structural properties as functions of cosmic time. The models predicted that galaxies at redshift 10^13 should be small, irregular, and metal-poor. Cosmic infants still in the early stages of development. Instead, JWST is showing us galaxies that appear mature, organized, and chemically evolved. The discrepancy isn't a matter of degree, but of fundamental character. Dr. Joel Primack, whose work on cold dark matter cosmology helped establish the Standard Model, acknowledges the severity of the challenge. These observations represent the most serious challenge to our understanding of galaxy formation since the field began. We're not talking about minor adjustments to our models. We're confronting the possibility that our fundamental assumptions are wrong. The tension between theory and observation has created what philosophers of science call a paradigm crisis. When well-established theories consistently fail to explain new observations, it signals that the field may be on the verge of a revolutionary transformation. The history of science is punctuated by such moments. The discovery of stellar aberration that challenged classical mechanics, the black-body radiation problem that led to quantum theory, the orbital precession of Mercury that pointed toward general relativity. But paradigm shifts in science aren't instantaneous or uniform. Different researchers respond to anomalous data in different ways. Conservative scientists double-check their measurements, look for systematic errors, and explore whether the existing theory might be salvaged with minor modifications. Progressive researchers embrace the anomaly as evidence for revolutionary change and begin developing alternative theories. In the current crisis, we see both responses at work. Some researchers are exploring whether improvements in modeling techniques, better treatment of stellar feedback, more sophisticated descriptions of gas cooling, or refined understanding of dark matter properties might explain the observations within the existing framework. Others are taking more radical approaches, questioning fundamental assumptions about the nature of dark matter, the properties of the early universe, or even the basic principles of structure formation. Some are exploring whether the laws of physics themselves might have been different when the universe was young. The philosophical implications are profound. Science operates on the assumption that the universe is comprehensible, that natural phenomena follow discoverable laws that can be expressed mathematically. When our best theories fail to predict observed phenomena, it challenges not just specific models, but the entire enterprise of scientific understanding. Yet history suggests that such crises are often precursors to breakthrough moments. The failure of classical physics to explain atomic phenomena led to quantum mechanics. The inability of Newton's laws to account for Mercury's orbit led to general relativity. Perhaps the failure of standard galaxy formation theory to explain these JWST observations will lead to an equally revolutionary advance in our understanding of the cosmos. Dr. Catherine Fries from UT Austin captures this optimistic perspective. These observations might be the universe's way of telling us we're ready for the next level of understanding. Every time we've been humbled by observational surprises, we've emerged with deeper insights into how reality works. The resolution of this crisis will likely require new physics, new mathematics, or entirely new ways of thinking about cosmic evolution. It might involve revisions to our understanding of dark matter, modifications to general relativity, or the discovery of previously unknown components of the universe. What's certain is that the comfortable period of consensus in cosmology is ending. The field is entering a new phase of uncertainty, debate, and exploration that could lead to fundamental breakthroughs in our understanding of the universe. As we stand at this crossroads, we're reminded that science is not a collection of established facts, but an ongoing dialogue between human curiosity and cosmic mystery. The universe has just spoken, and what it's saying challenges everything we thought we knew about how galaxies form and evolve. When faced with observations that seem to overturn decades of established science, the first instinct of any responsible researcher is to question the measurements themselves. Could these impossibly mature early galaxies be the result of systematic errors, calibration problems, or misinterpretation of complex data? The scientific method demands such skepticism, and several teams have devoted enormous effort to testing whether the JWST discoveries might be elaborate measurement mistakes. The most obvious concern involves distance determination, the fundamental measurement that tells us how far back in time we're looking. Astronomical distances are notoriously difficult to measure accurately, especially for the most distant objects. The primary method used for these early galaxies relies on photometric redshifts, estimates based on the colors of galaxies as observed through different filters. Dr. Stephen Finkelstein from UT Austin, who leads one of the major JWST survey teams, explains the challenge. Determining accurate distances to these early galaxies is like trying to judge how far away a car is at night, based only on the color of its headlights. Small errors in our assumptions about the galaxy's properties can lead to large errors in distance estimates. The photometric redshift technique works by comparing the observed colors of distant galaxies to templates of how galaxy colors should change with redshift. But these templates are based on observations of more recent galaxies, and if early galaxies had significantly different properties than their modern counterparts, the technique could systematically overestimate their distances. Some researchers initially proposed that these early galaxies might actually be much closer, perhaps heavily dust-obscured galaxies from more recent cosmic epochs, whose unusual colors mimic the signatures of extreme redshift. Dust can preferentially absorb blue light while allowing red light to pass through, potentially creating color signatures that could be mistaken for cosmological redshift. However, spectroscopic follow-up observations have largely ruled out this explanation. When JWST's spectrographs spread the light from these galaxies into their component wavelengths, they reveal the characteristic patterns of highly redshifted hydrogen and other elements. However, spectroscopic follow-up observations have largely ruled out this explanation. These spectroscopic redshifts are far more reliable than photometric estimates and consistently confirm the extreme distances and early cosmic ages of these galaxies. Another potential source of error involves the mass estimates themselves. Determining how many stars a galaxy contains requires converting observed light into stellar mass, a process that depends on assumptions about the galaxy's stellar population, star formation history, and internal dust content. Another potential source of error involves the mass estimates themselves. If early galaxies had dramatically different properties than assumed, perhaps forming unusually massive stars or experiencing exotic phases of evolution, the mass estimates could be significantly wrong. Dr. Marijn Franks from Leiden University, who has spent decades refining techniques for measuring galaxy properties, acknowledges the complexity. Every measurement in extragalactic astronomy involves a chain of assumptions. If any link in that chain is wrong, the final result can be dramatically off. We've learned to be extremely cautious about extraordinary claims. Some researchers have also questioned whether instrumental effects might be responsible for the apparent maturity of these early galaxies. JWST's unprecedented sensitivity and resolution reveal structural details in distant galaxies that were invisible to previous telescopes. So Rezenauf the Rezen Summer C, if you Summer C run Genscher. Some researchers have also questioned whether instrumental effects might be responsible for the apparent maturity of these early galaxies. Could features that appear to indicate organized galaxy structure actually be artifacts of the telescope's point spread function or image processing algorithms? Extensive tests using simulated galaxy images have largely ruled out this possibility. The structural features observed in these early galaxies, rotation patterns, spiral arms, and disk-like morphologies, appear to be real rather than instrumental artifacts. Extensive tests using simulated galaxy images have largely ruled out this possibility. Independent analysis teams using different data reduction techniques consistently recover similar structural properties. Perhaps the most thorough test of the measurement mistake hypothesis has come from the consistency of results across multiple independent surveys. The JD's team, the Sears collaboration, the GLASS survey, and several other groups have all identified similar populations of unusually mature early galaxies using different instruments, different observing strategies, and different analysis techniques. Dr. Tommaso True, from UCLA, who coordinates several of these survey efforts, summarizes the situation. When multiple independent teams using different methods all reach similar conclusions, it becomes increasingly difficult to attribute the results to measurement errors. The observations appear to be robust. While measurement uncertainties undoubtedly contribute to some of the apparent extremes in these early galaxy properties, they cannot explain away the fundamental challenge these objects pose to our understanding of cosmic evolution. The systematic nature of the discrepancies, confirmed across multiple independent observations, suggests that we're confronting a genuine phenomenon rather than a measurement artifact. With a measure, if these early galaxies are real, then the universe must have possessed mechanisms for accelerated evolution that our current models don't account for. Theoretical astrophysicists are exploring several exotic possibilities that might explain how cosmic structures could develop so rapidly in the early universe, each requiring us to push the boundaries of known physics. One intriguing possibility involves primordial density fluctuations, far more extreme than anything predicted by standard inflation models. If certain regions of the early universe were significantly denser than average, they could have collapsed and begun forming stars much earlier than expected. These overdense regions might have acted as cosmic nurseries, accelerating every aspect of galaxy formation, from initial star formation to chemical enrichment. Dr. Abraham Loeb from Harvard proposes that rare extreme density peaks in the early universe could have triggered what he calls runaway structure formation. In these special regions, the normal timescales for stellar evolution, chemical enrichment, and dynamical relaxation might have been compressed by factors of 10 or more. Think of it as cosmic time-lapse photography, Loeb explains. Processes that normally take billions of years could have occurred in just hundreds of millions of years under the right conditions. Another possibility involves exotic phases of stellar evolution that might have operated only in the early universe. The first generation of stars, population 3 stars, formed from pristine hydrogen and helium gas with no heavy elements. These primordial conditions might have allowed for stellar formation and evolution processes that no longer occur in the modern universe. Some researchers propose that early stars might have formed with dramatically different mass distributions than modern stellar populations. If the early universe preferentially produced intermediate mass stars, objects too small to explode as supernovae, but large enough to evolve rapidly, they could have enriched their environments with heavy elements much more efficiently than the massive population 3 stars traditionally assumed. Dr. Raffaele Schneider from the University of Rome has developed models suggesting that early stellar populations might have included a much higher fraction of very massive stars, objects with 100–300 solar masses, that would have lived for only a few million years before exploding as hypernova. These stellar giants could have rapidly enriched their surroundings, while also providing the intense radiation fields necessary to trigger subsequent generations of star formation. The role of supermassive black holes in accelerating early galaxy evolution represents another frontier of theoretical exploration. Rather than growing slowly from stellar remnants, these early black holes might have formed through direct collapse of massive gas clouds in the early universe. Such direct collapse black holes could begin with masses of 10,000, 100,000 solar masses, providing a significant head start in the race to build supermassive objects. Once formed, these early black holes might have played crucial roles in regulating and accelerating star formation in their host galaxies. The jets and outflows from actively feeding black holes can compress surrounding gas, potentially triggering intense bursts of star formation. This feedback mechanism could create a positive feedback loop where rapid star formation feeds the central black hole, which in turn triggers even more star formation. Dr. Marta Volnteri, from the Institut d'Astrophysique de Paris, has developed sophisticated models of early black hole formation and growth. Her work suggests that under the extreme conditions of the early universe, black holes could have grown much more rapidly than previously thought possible. The early universe might have been a perfect storm for black hole formation and growth, she explains. High gas densities, minimal stellar feedback, and exotic formation mechanisms could have led to rapid assembly of supermassive objects. Another exotic possibility involves modifications to the physics of star formation itself. In the dense, metal-free environment of the early universe, the process of gas cooling and fragmentation might have operated differently than in modern star-forming regions. Some models suggest that early star formation could have been far more efficient, converting a much higher fraction of available gas into stars. The magnetic field environment of the early universe might also have played a role in accelerating galaxy formation. Primordial magnetic fields, possibly generated during cosmic inflation or phase transitions in the early universe, could have influenced the collapse of gas clouds and the subsequent process of star formation in ways that our current models don't account for. Dark matter itself might have behaved differently in the early universe. Some theories propose that dark matter particles could have had stronger self-interactions when the universe was denser and hotter, potentially leading to more rapid collapse and concentration. Alternatively, interactions between dark matter and ordinary matter might have been stronger in the past, accelerating the formation of the first structures. Perhaps most speculatively, some researchers are exploring whether the fundamental constants of physics might have had different values in the early universe. If the strength of gravity, the efficiency of nuclear fusion, or the properties of electromagnetic interactions were slightly different billions of years ago, it could explain the rapid evolution observed in these early galaxies. Dr. Joe Magajo from Imperial College London, known for his work on varying fundamental constants, suggests that the universe might have been more impatient when it was young. If physical processes operated faster in the early universe, it could naturally explain these mature early galaxies without requiring exotic astrophysical mechanisms. While these explanations remain highly speculative, they represent serious attempts by the theoretical community to understand how the universe could have evolved so rapidly in its youth. The challenge is developing models that can account for the JWST observations, while remaining consistent with everything else we know about physics and astronomy. Among all the potential explanations for these impossibly mature early galaxies, one stands out as both elegant and revolutionary: primordial black holes. These hypothetical objects, formed not from the collapse of stars, but from extreme density fluctuations in the very early universe, could potentially solve multiple puzzles simultaneously. They might explain how supermassive black holes grew so quickly, how galaxies assembled so rapidly, and why the early universe was so much more active than our models predicted. The concept of primordial black holes dates back to the 1970s, when Stephen Hawking and Bernard Carr first proposed that regions of extreme density in the early universe could have collapsed directly into black holes without ever forming stars. Unlike stellar black holes, which are limited by the masses of their progenitor stars, primordial black holes could have formed with a wide range of masses, from microscopic objects smaller than atoms to supermassive giants, rivaling those found at the centers of modern galaxies. The formation mechanism is conceptually straightforward, but requires extreme conditions. In the first moments after the Big Bang, quantum fluctuations inflated to cosmic scales could have created regions where matter was compressed to densities far exceeding anything found in normal stellar cores. If these density fluctuations exceeded a critical threshold, roughly 30% above the average density, they could have collapsed directly into black holes without ever forming stars or galaxies. Dr. Bernard Carr, from Queen Mary University of London, One of the pioneering researchers in this field explains the significance primordial black holes represent a completely different pathway to forming massive objects in the early universe. Instead of waiting for stars to form, live, and die, you could have massive black holes appearing almost immediately after the Big Bang. The implications for early galaxy formation are profound. If primordial black holes with masses of thousands to millions of solar masses peppered the early universe, they would have acted as gravitational seeds around which the first galaxies could assemble. These black holes would have been preloaded with significant mass, eliminating the lengthy growth phase that makes stellar origin supermassive black holes so problematic in the early universe. Moreover, the intense gravitational fields of these primordial black holes could have accelerated every aspect of early structure formation. Gas falling toward these objects would have been heated and compressed, potentially triggering intense bursts of star formation in their immediate vicinity. The feedback from these active galactic nuclei could have driven powerful winds that distributed heavy elements throughout the forming galaxy, accelerating chemical evolution. Recent theoretical work by Dr. Priyamvada Natarajan at Yale University suggests that primordial black holes could explain not just the rapid formation of supermassive black holes, but also the tight correlations observed between black hole masses and their host galaxy properties. If galaxies formed around pre-existing black hole seeds, the final mass of both the black hole and the galaxy would be determined by the same reservoir of infalling material, naturally explaining why these objects appear to know about each other's properties. The primordial black hole hypothesis also addresses the timing problems that plague conventional galaxy formation models. Instead of requiring multiple generations of stellar evolution to build up heavy elements, a galaxy forming around a primordial black hole could achieve chemical maturity much more rapidly. The black hole's powerful radiation field would drive intense star formation in the surrounding gas, while its gravitational influence would help organize stellar orbits into the coherent structures observed in these early systems. But perhaps most intriguingly, primordial black holes might help explain why the early universe appears so much more active than expected. If substantial numbers of these objects formed in the first moments after the Big Bang, they would have begun accreting matter and powering active galactic nuclei much earlier than conventional models allow. The cumulative effect of millions of these early quasars could have ended the cosmic dark ages much sooner than predicted, beginning the process of reionizing the universe when it was only a few 100 million years old. The observational signatures of primordial black hole-seeded galaxy formation might be detectable with current instruments. Galaxies forming around massive black hole seeds should show distinctive properties in their stellar populations, chemical abundance patterns, and structural characteristics. With as observational signatures of primordial black hole-seeded galaxy formation might be detectable with current instruments, some researchers argue that the unusual properties observed in these early JWST galaxies, their high stellar masses, organized structures, and chemical maturity, are exactly what we would expect from primordial black hole-seeded formation. Dr. Nico Capilouti from the University of Miami has been investigating the observational consequences of primordial black hole scenarios. His work suggests that the X-ray signatures from early active galactic nuclei powered by primordial black holes should be detectable with future missions. Dr. Nico Capilouti from the University of Miami has been investigating the observational consequences of primordial black hole scenarios. We're looking for the smoking gun that would confirm primordial black holes played a role in early galaxy formation, he explains. The signatures should be distinctive and observable. However, the primordial black hole solution isn't without challenges. For these objects to form in sufficient numbers to explain the JWST observations, the early universe would need to have had much larger density fluctuations than predicted by standard inflation models. This might require exotic inflation scenarios or additional physics operating in the very early universe. The survival of primordial black holes through cosmic history also presents theoretical challenges. Hawking radiation causes black holes to evaporate over time, with the evaporation rate inversely related to their mass. Holes in distum. In the survival of primordial black holes through cosmic history also present distum. Only primordial black holes more massive than about 10 circumflex 15 grams, roughly the mass of a mountain, could have survived to the present day. This constraint limits the possible mass range for primordial black holes that could have influenced early galaxy formation. Furthermore, if primordial black holes were common enough to explain rapid early galaxy formation, they should have left detectable signatures in other cosmological observables. The gravitational wave signals from primordial black hole mergers, the effects on Big Bang nucleosynthesis, and the influence on cosmic microwave background fluctuations all provide potential tests of these scenarios. Furthermore, if primordial black holes were common enough to explain rapid early galaxy formation, they should have left detectable signatures in other cosmological observables. Recent advances in gravitational wave astronomy have opened new windows for detecting primordial black holes. The merger events detected by LIGO and Virgo might include some primordial black hole pairs, and future space-based detectors, like LISA, will be sensitive to the characteristic signatures of these exotic objects. As Dr. Misao Sasaki from the University of Tokyo observes, primordial black holes represent one of the most elegant solutions to the early galaxy formation puzzle. They could simultaneously explain the rapid assembly of supermassive black holes, the accelerated evolution of early galaxies, and the unexpected activity level of the early universe. The challenge now is to develop definitive observational tests that can confirm or rule out their role in cosmic evolution. Einstein called it his greatest blunder, cosmological constant he introduced into his equations of general relativity to maintain a static universe. When Edwin Hubble discovered cosmic expansion, Einstein abandoned the constant, believing it was no longer needed. But in one of science's greatest ironies, the cosmological constant returned with a vengeance in 1998, when astronomers discovered that the universe's expansion is accelerating, driven by the mysterious force we now call dark energy. Today, as JWST reveals impossibly mature galaxies in the early universe, we're confronting what might be an even deeper crisis involving Einstein's cosmological constant and our understanding of cosmic evolution. These discoveries suggest that the universe evolved far more rapidly in its youth than our current models predict, potentially requiring fundamental revisions to our understanding of space-time, gravity, and the forces that shape cosmic history. The cosmological constant, represented by the Greek letter lambda, describes the energy density of empty space itself. In Einstein's equations, it acts as a repulsive force that counteracts gravity on cosmic scales. Modern observations suggest this dark energy comprises roughly 68% of the universe's total energy budget, yet its physical nature remains one of the deepest mysteries in physics. The standard lambda CDM model, lambda cold dark matter, incorporates this cosmological constant as a fixed parameter that has remained unchanged throughout cosmic history. This model successfully explains the large-scale structure of the universe, the cosmic microwave background, and the observed acceleration of cosmic expansion. But it predicts a specific timeline for structure formation that appears incompatible with the JWST discoveries. Dr. Adam Riess, who shared the Nobel Prize for discovering cosmic acceleration, frames the challenge. Our models predict that dark energy has been the dominant component of the universe for only the last few billion years. In the early universe, matter should have dominated, and structure formation should have proceeded at predictable rates. These mature early galaxies suggest something was different about how the universe evolved when it was young. One radical possibility is that the cosmological constant itself has evolved over cosmic time. If dark energy was stronger in the early universe, it could have influenced structure formation in unexpected ways. A higher dark energy density in the past might have created conditions that accelerated the collapse of matter into the first galaxies, compressed the timescales for stellar evolution, or altered the physics of black hole formation and growth. This scenario, known as dynamical dark energy, would require abandoning one of the fundamental assumptions of the lambda CDM model, that the cosmological constant is truly constant. Instead, dark energy would be described by a field that changes over time, similar to the inflatone field, thought to drive cosmic inflation in the very early universe. Dr. Sean Carroll from Caltech, a leading theoretical cosmologist, explains the implications. If dark energy has evolved significantly over cosmic time, it would require us to reconsider everything we think we know about the universe's history, the timeline of structure formation, the age of the universe, and even the ultimate fate of the cosmos could all be different than we currently believe. The mathematical consequences of time-varying dark energy are profound. In standard cosmology, the expansion history of the universe follows a predictable pattern. An early period dominated by radiation, followed by matter domination, and finally, the current epoch of accelerating expansion driven by dark energy. But if dark energy was stronger in the past, this neat division into distinct epochs breaks down. A more active dark energy in the early universe could have created what cosmologists call early dark energy scenarios. In these models, dark energy contributes a significant fraction of the universe's energy density, even in the first billion years after the Big Bang. This early dark energy could have influenced the formation of the first structures, potentially explaining how galaxies could assemble so much more rapidly than current models predict. However, early dark energy scenarios face significant observational constraints. The cosmic microwave background provides an exquisitely detailed snapshot of the universe when it was only 380,000 years old. Any significant dark energy component at that time would have left distinctive signatures in the temperature and polarization patterns of this ancient light. Current observations of the CMB appear to rule out substantial early dark energy, creating a tension between what the CMB allows and what the JWST observations seem to require. Some researchers are exploring whether more exotic forms of dark energy might resolve this tension. Rather than a simple cosmological constant, dark energy might be described by a dynamic field with complex interactions, telluri, that change its behavior over cosmic time. These quintessence models allow for dark energy that strengthens and weakens in response to the evolving density and temperature of the universe. Dr. Robert Caldwell from Dartmouth College, who pioneered much of the theoretical work on dynamical dark energy, describes the challenge. We need forms of dark energy that can remain nearly invisible to CMB observations, while still providing enough influence in the early universe to explain rapid galaxy formation. It's a very narrow parameter space, but it might be possible. Another possibility involves modifications to Einstein's theory of general relativity itself. While general relativity has passed every experimental test in the solar system and strong gravitational fields, its behavior on cosmic scales remains less well constrained. Some modified gravity theories predict different expansion histories and structure formation timelines that might explain the JWST observations without requiring exotic dark energy. The implications of revising our understanding of dark energy extend far beyond just explaining early galaxy formation. Dark energy determines the ultimate fate of the universe, whether it will expand forever, reach a maximum size and contract, or experience more exotic scenarios like a big rip where the fabric of space-time itself tears apart. If dark energy has evolved over cosmic time, it might continue to evolve in the future, leading to dramatically different cosmic destinies than current models predict. The universe might experience periods of deceleration, followed by acceleration, cycles of expansion and contraction, or transitions to entirely different phases of cosmic evolution. The JWST discoveries are forcing cosmologists to confront the possibility that our understanding of the universe's expansion history is incomplete. The crisis extends beyond just galaxy formation to the fundamental physics of space-time, energy, and the forces that govern cosmic evolution. We may be witnessing the beginning of a revolution in cosmology, as profound as Einstein's original introduction of the cosmological constant over a century ago. Einstein's theory of general relativity has reigned supreme for over a century, successfully predicting everything from the precession of Mercury's orbit to the existence of gravitational waves. Yet, as JWST reveals galaxies that shouldn't exist according to our models, Some physicists are wondering whether Einstein's equations might need modification to explain how cosmic structures could form so rapidly in the early universe. Modified gravity theories represent some of the most radical solutions to the early galaxy formation puzzle. Rather than invoking exotic forms of matter or energy, these approaches suggest that gravity itself might behave differently than Einstein predicted, particularly on cosmic scales or in the extreme conditions of the early universe. The motivation for considering modified gravity extends beyond just the JWST discoveries. For decades, astronomers have encountered phenomena that seem to require invisible components, dark matter, and dark energy, to explain within the framework of general relativity. Dark matter, supposedly 5 times more abundant than ordinary matter, has never been directly detected despite intensive searches. Dark energy, which drives cosmic acceleration, remains even more mysterious. Dr. Stacy McGaw from Case Western Reserve University, a leading advocate for modified gravity approaches, frames the challenge. We keep discovering that the universe doesn't behave as Einstein's equations predict, unless we add components we can't see or detect. At some point, we need to consider whether the problem isn't missing matter and energy, but missing physics. One class of modified gravity theories, known as FR gravity, proposes that Einstein's equations become modified when the curvature of spacetime becomes extreme. In regions of high curvature, such as the dense environments where the first galaxies formed, gravity might become stronger than Einstein predicted, accelerating the collapse of matter and the formation of structures. These theories suggest that in the early universe, when matter densities were much higher than today, gravity could have operated in a regime where Einstein's equations break down. The enhanced gravitational attraction could have pulled matter together more rapidly, compressed the timescales for star formation, and accelerated the assembly of massive galaxies. Dr. Claudia de Ram, from Imperial College London, who has made fundamental contributions to modified gravity theory, explains the concept. Think of Einstein's gravity as the limiting case of a more general theory, similar to how Newton's laws emerge as the slow speed limit of special relativity. In the extreme conditions of the early universe, we might be seeing gravity operating in a regime where its true nature becomes apparent. Another approach, called scalar tensor gravity, introduces additional fields that can modify gravitational interactions depending on local conditions. These theories allow gravity to have different strengths in different environments or at different times in cosmic history. In the dense, rapidly evolving conditions of early galaxy formation, these scalar fields might have enhanced gravitational attraction, explaining how structures could assemble so much more quickly than standard general relativity allows. The theoretical framework of emergent gravity takes an even more radical approach, suggesting that gravity itself might be an emergent phenomenon that arises from more fundamental physics. In these models, the strength and behavior of gravity could depend on the amount of entropy or information in a given region of spacetime. The early universe, with its extreme conditions and rapid evolution, might have experienced gravitational effects that don't occur in the more sedate conditions of the modern cosmos. Dr. Erik Verlinde, from the University of Amsterdam, whose work on emergent gravity has garnered significant attention, proposes that gravity might be fundamentally different in environments undergoing rapid change or extreme density contrasts. The early universe represents exactly such an environment, where our usual understanding of gravitational physics might not apply. Extra-dimensional theories provide another avenue for modifying gravity's behavior. If our three-dimensional space is embedded in higher-dimensional spacetime, gravity could leak into these extra dimensions, changing its strength and behavior under certain conditions. In the compact, high-energy environment of the early universe, these extra-dimensional effects might have been more pronounced, leading to enhanced structure formation. Modified gravity theories also offer potential explanations for the rapid growth of supermassive black holes in early galaxies. If gravity was stronger in the past, it could have enabled more rapid accretion of matter onto black holes, accelerating their growth beyond the limits imposed by standard general relativity and the Eddington limit. However, modified gravity theories face significant observational challenges. Any modification to Einstein's equations must explain not only the rapid formation of early galaxies, but also reproduce all the successful predictions of general relativity in other contexts. The theory must account for the precise predictions of Big Bang nucleosynthesis, the detailed patterns in the cosmic microwave background, and the successful tests of general relativity in the solar system. Dr. Antonio de Felice from Kyoto University, who works on observational tests of modified gravity, describes the challenge. Modified gravity theories must walk a very fine line. They need to be different enough to explain the JWST observations, but similar enough to Einstein's theory to match everything else we observe. It's a narrow target to hit. Recent advances in gravitational wave astronomy provide new ways to test modified gravity theories. If gravity behaved differently in the past, it might have left signatures in the gravitational wave background that permeates the universe. Future space-based detectors will be sensitive enough to detect these primordial gravitational waves, potentially providing direct evidence for or against modified gravity scenarios. The stakes of this investigation extend far beyond explaining early galaxy formation. If gravity itself operates differently than Einstein predicted, it would represent one of the most profound revolutions in physics since the development of quantum mechanics and relativity. Perhaps the most mind-bending potential explanation for these impossibly mature early galaxies lies not in modifying our understanding of physics within our universe, but in recognizing that our universe might be just one of countless others, each with slightly different properties that could explain why cosmic evolution proceeded so rapidly in the early epochs we're observing. The multiverse hypothesis suggests that what we call the universe is actually just one bubble in an infinite cosmic foam, where each bubble represents a separate universe with its own unique set of physical laws, fundamental constants, and initial conditions. In this framework, the rapid galaxy formation observed by JWST might not require exotic physics or modifications to well-tested theories. It might simply reflect the fact that we happen to live in a universe where the conditions were particularly favorable for accelerated cosmic evolution. Dr. Max Tegmark from MIT, one of the leading proponents of multiverse cosmology, explains the concept. If there are infinite universes with varying properties, then somewhere there must be universes where galaxy formation proceeded much more rapidly than our models predict. The JWST discoveries might be showing us that we live in exactly such a universe. The theoretical foundation for the multiverse emerges naturally from our best models of cosmic inflation, the period of exponential expansion thought to have occurred in the first fraction of a second after the Big Bang. Inflation theory predicts that this rapid expansion created not just our observable universe, but countless other regions of space-time, each potentially inflating into its own separate universe with unique properties. In the eternal inflation scenario, developed by physicists like Alan Guth and Andre Linde, the inflaton field that drives cosmic expansion behaves differently in different regions of space-time. Some regions stop inflating and form universes like ours, while others continue expanding, constantly spawning new universe bubbles with randomly varying physical properties. This process would create an infinite collection of universes with different values for fundamental constants like the strength of gravity, the mass of elementary particles, or the density of dark matter. Most of these universes would be hostile to the formation of complex structures. Some would collapse immediately, others would expand so rapidly that matter could never clump together. Still others would lack the right conditions for star formation. But in a tiny fraction of these universes, the conditions would be just right for rapid structure formation. Perhaps gravity would be slightly stronger, allowing matter to collapse more quickly. Perhaps the initial density fluctuations would be larger, providing bigger seeds for galaxy formation. Perhaps the properties of dark matter would favor faster assembly of cosmic structures. The anthropic principle provides a framework for understanding why we might find ourselves in such a special universe. We can only observe universes that are capable of producing observers like ourselves. If rapid early galaxy formation is somehow necessary for the eventual emergence of life and intelligence, then we would necessarily find ourselves in a universe where such rapid formation occurred, regardless of how improbable it might seem from a purely physical perspective. Dr. Steven Weinberg, Nobel laureate and pioneer of the anthropic approach to cosmology, argued that the apparent fine-tuning of physical constants and initial conditions might not require exotic explanations, if we accept that we can only observe universes compatible with our existence. This deck, Muimte, would serve universes compatible with our existence. The JWST discoveries might simply be showing us another aspect of the cosmic conditions that made our existence possible. However, the multiverse explanation for rapid early galaxy formation faces significant philosophical and scientific challenges. Heretics argue that the multiverse hypothesis is inherently unscientific because it makes no testable predictions and cannot be falsified through observation. If anything unexpected can be explained by appealing to other universes with different properties, the hypothesis loses its explanatory power. Furthermore, the multiverse approach doesn't necessarily solve the timing problems posed by the JWST observations. Even in a universe with slightly different physical constants, the fundamental processes of stellar evolution, chemical enrichment, and structure formation would still require specific amounts of time to complete. Explaining the extreme rapidity of early galaxy formation might require such dramatic changes to physical laws that the resulting universe would be unrecognizable. Some researchers argue that the multiverse hypothesis represents a retreat from the scientific goal of understanding why our universe has the properties it does. Rather than seeking physical explanations for cosmic phenomena, the multiverse approach explains them as random outcomes in an infinite ensemble of possibilities. As Dr. Paul Steinhardt from Princeton University observes, the multiverse might be real, but invoking it to explain every unexpected observation is abandoning the scientific enterprise of finding deeper physical principles that govern cosmic evolution. Behind every revolutionary scientific discovery lies a human story of curiosity, perseverance, and the courage to question established wisdom. The JWST discoveries that are challenging our understanding of the early universe emerged from the dedication of astronomers who spent decades planning observations, developing new techniques, and pushing the boundaries of what seemed possible. Their story is one of scientific ambition on a scale that spans generations. Dr. Brant Robertson from UC Santa Cruz represents the new generation of astronomers who grew up knowing that JWST would eventually launch. As a graduate student in the early 2000s, he watched the telescope's development with a mixture of excitement and impatience. Dr. Brant Robertson from UC Santa Cruz represents the new generation of astronomers who grew up knowing said, "I remember calculating that if everything went perfectly, JWST might launch just as I was finishing my PhD." Robertson recalls, "It seemed like this amazing instrument was always just a few years away." Robertson's early career was shaped by preparing for JWST's eventual arrival. He specialized in theoretical models of early galaxy formation, developing sophisticated computer simulations that predicted what the telescope should see when it finally reached the depths of cosmic time. His models suggested that early galaxies would be small, irregular, and relatively rare, predictions that would soon be overturned by the very instrument he had spent years preparing to use. The human dimension of the JWST project extends far beyond individual researchers to encompass entire careers dedicated to a single goal. Dr. Marcia Ricci, from the University of Arizona, began working on what would eventually become JWST's near-infrared camera in the 1990s. Over 2 decades, she navigated budget crises, technical setbacks, and political challenges that repeatedly threatened the project's survival. There were times when it seemed like JWST might never launch. Reek remembers, "We had members of Congress calling it a waste of taxpayer money and budget committees, threatening cancellation. But we knew the science would be revolutionary if we could just make it work." Her persistence through decades of uncertainty reflects the deep commitment required for transformational scientific projects. The diversity of the discovery team reflects the global nature of modern astronomy. Dr. Emma Curtis Lake from the University of Hertfordshire brought expertise in spectroscopic analysis of distant galaxies. Dr. Stefano Carniani from the University of Cambridge contributed theoretical insights into early galaxy formation. Dr. Kevin Heinlein from the University of Arizona provided crucial experience in infrared observations and data analysis. Each team member brought unique skills developed over years of preparation for JWST's arrival. The collaboration required not just scientific expertise, but also diplomatic skills to coordinate observations across different institutions, time zones, and scientific cultures. The challenge of managing large international collaborations while maintaining scientific rigor adds a human dimension, often invisible in published research papers. The moment of discovery itself was both anticlimactic and electrifying. Daniel Eisenstein, from Harvard-Smithsonian, who leads the JDIS survey, describes the initial reaction. We were looking at the first images, and someone said, "That galaxy looks awfully bright for something supposedly so far away." It was one of those moments where you realize the data is telling you something unexpected. The initial response was skepticism, a healthy scientific instinct when confronted with observations that challenge fundamental assumptions. The team spent weeks double-checking their analysis, rerunning their calculations, and searching for possible errors. The discovery process wasn't a single eureka moment, but a gradual realization that the universe was refusing to conform to their expectations. Dr. Sandro Tacella from Cambridge University, who contributed crucial analysis of the galaxy's structural properties, captures the emotional complexity of revolutionary discoveries. Part of you is excited because you're seeing something unprecedented, but another part is terrified because it means everything you thought you understood might be wrong. It's simultaneously thrilling and unsettling. The personal stakes for these researchers are enormous. Many built their careers on theoretical models that the JWST observations appear to contradict. Rather than defensively protecting their previous work, most have embraced the challenge of revising their understanding based on new evidence, a testament to the intellectual honesty that defines good science. The generational aspect of the discovery adds another layer to the human story. Senior researchers who develop the theoretical framework for galaxy formation find themselves working alongside graduate students who take JWST's capabilities for granted. This mixing of perspectives, established wisdom confronting fresh viewpoints, often catalyzes scientific breakthroughs. Dr. Roberto Maiolino from Cambridge, whose spectroscopic work confirmed the extreme distances of these early galaxies, reflects on the collaborative nature of the discovery. No single person could have made these discoveries alone. It required decades of work by hundreds of people. Engineers who built the telescope, theorists who developed the models, observers who planned the surveys, and data analysts who extracted meaning from the observations. The global COVID-19 pandemic added unexpected challenges to the discovery process. Much of the initial analysis was conducted with team members scattered across different continents, collaborating through video conferences and shared computer screens. The isolation imposed by pandemic restrictions may have actually enhanced focus on the data analysis, but it also deprived researchers of the informal discussions and chance encounters that often spark scientific insights. As news of the discoveries began to spread through the astronomical community, the researchers found themselves at the center of intense scientific and media attention. The responsibility of communicating revolutionary findings to both scientific peers and the public adds pressure to an already complex situation. The path from initial observation to accepted scientific revolution is never smooth, and the JWST discoveries have triggered one of the most intense debates in modern cosmology. What began as curious anomalies in telescope data has evolved into a full-scale challenge to cosmological orthodoxy, complete with passionate defenders of established theory and bold advocates for revolutionary change. The initial scientific papers describing these mature early galaxies were met with a reception that can only be described as turbulent. Peer reviewers struggled with how to evaluate claims that seemed to contradict decades of established science. Some reviewers demanded additional verification, others questioned the methodology, and a few simply rejected the conclusions as too extraordinary to believe. Dr. Casey Papovich from Texas A&M University, who served as a reviewer for several of these groundbreaking papers, describes the challenge. How do you review a paper that claims to overturn fundamental assumptions about cosmic evolution? Your instinct is to be skeptical, but you also have to remain open to the possibility that the universe is stranger than we thought. The astronomical community's response reflected the classic stages of scientific paradigm shifts described by philosopher Thomas Kuhn. Initial denial gave way to attempts to explain the observations within existing frameworks, followed by growing acceptance that something fundamental might need to change. Conference presentations became battlegrounds, where different interpretations clashed. At the American Astronomical Society meeting in Seattle, sessions on early galaxy formation drew standing-room-only crowds as researchers debated the implications of the JWST findings. The usually polite discourse of academic astronomy gave way to passionate exchanges that sometimes bordered on confrontational. Dr. Sandra Faber from UC Santa Cruz, whose work on galaxy evolution spans 4 decades, witnessed the controversy from a unique perspective. I've seen several major upheavals in astronomy during my career, but this feels different. The observations are so clear, and the implications so profound, that you can't just ignore them or explain them away. The debate quickly spread beyond specialist conferences to the broader scientific community. Social media platforms buzzed with discussions about whether the Big Bang theory was wrong or merely incomplete. Science journalists found themselves trying to explain complex cosmological concepts to audiences hungry for sensational headlines about revolutionary discoveries. This public attention added pressure to the scientific debate. Researchers found themselves defending not just their specific findings, but the entire process of scientific inquiry. Critics outside the scientific community seized on the controversy as evidence that scientists don't know what they're talking about, while supporters argued that this willingness to revise understanding based on new evidence demonstrated science at its best. The generational divide within astronomy became apparent during these debates. Younger researchers, who had grown up with the expectation that JWST would reveal surprises, seemed more willing to embrace radical interpretations. Senior astronomers, who had spent careers developing the models now under challenge, showed more resistance to revolutionary explanations. Dr. Joel Primack, from UC Santa Cruz, one of the architects of modern cosmological theory, admits to the psychological difficulty of seeing his life's work questioned. It's humbling to realize that theories you've spent decades developing might need fundamental revision, but that's how science works. Observations trump theory, no matter how elegant or well-established the theory might be. The institutional pressures surrounding the controversy created additional complications. Graduate students found themselves in awkward positions when their thesis advisors disagreed with other faculty members about the interpretation of the data. Of the interpretation of the data, funding agencies had to decide whether to support research based on controversial findings. Journal editors struggled with how to handle papers that challenged fundamental assumptions. Some researchers adopted a cautious middle ground, arguing that while the observations were intriguing, more data was needed before drawing revolutionary conclusions. Others embraced the controversy, seeing it as an opportunity to develop new theoretical frameworks that could explain both the JWST observations and everything else we know about the universe. The international nature of modern astronomy complicated the debate, as different scientific cultures approached the controversy with varying degrees of skepticism and openness to radical change. European researchers, working within a tradition that emphasized theoretical rigor, sometimes clashed with their American counterparts, who placed greater emphasis on observational discoveries. Perhaps most significantly, the controversy has revealed the deep philosophical assumptions underlying modern cosmology. The debate isn't just about specific observations or theoretical models. It's about how we understand the nature of scientific truth and the process by which established theories get replaced by new ones. As the controversy continues to unfold, it's becoming clear that regardless of the ultimate resolution, the JWST discoveries have already transformed the field of cosmology by forcing researchers to confront the limits of their understanding and the assumptions underlying their models. Every scientific revolution builds upon the accumulated wisdom of previous generations, and the JWST discoveries that are challenging our understanding of the early universe represent the culmination of nearly a century of cosmological research. Semwende Itures Pielvert. To understand the full significance of these findings, we must trace the intellectual lineage that led to our current crisis in cosmology, a lineage that reveals how science progresses through both confirmation and contradiction of established ideas. The story begins with Edwin Hubble's revolutionary observations in the 1920s that revealed the expansion of the universe. Working with the 100-inch telescope at Mount Wilson Observatory, Hubble discovered that distant galaxies were receding from us at velocities proportional to their distances. This observation provided the first direct evidence for what would become known as the Big Bang theory, establishing the conceptual framework within which all subsequent cosmological research would operate. But Hubble's work also established the methodological foundations that make the current JWST discoveries possible. His techniques for measuring galactic distances, determining recession velocities, and relating observational data to cosmological models created the analytical toolkit that modern astronomers still use. The redshift measurements that allow us to peer deep into cosmic time are direct descendants of Hubble's pioneering observations. The theoretical framework for understanding cosmic evolution emerged through the work of brilliant minds like Alexander Friedmann, Georges Lemaire. Friedmann's solutions to Einstein's field equations showed how the universe could expand or contract, providing the mathematical foundation for modern cosmology. Lemaire, often called the father of the Big Bang theory, proposed that the universe began in what he poetically termed the primeval atom, a concentrated state from which all cosmic structure emerged. Gamo's contributions were particularly crucial for understanding the current crisis. His work on Big Bang nucleosynthesis predicted the formation of light elements in the early universe, while his insights into stellar evolution established the timescales that make the JWST observations so puzzling. The theoretical framework that predicts slow, gradual galaxy formation is built directly on Gamo's understanding of stellar physics and nuclear processes. The discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided crucial confirmation of Big Bang cosmology, but it also established observational constraints that any new theory must satisfy. The exquisite uniformity of this ancient light, combined with tiny fluctuations that seed later structure formation, creates boundary conditions that limit how dramatically we can revise our understanding of cosmic evolution. Ralph Alpha and Robert Herman, working with Gamo, made predictions about the temperature and properties of the cosmic microwave background that were confirmed decades later. Their work established the observational tests that any alternative cosmological theory must pass, tests that make it challenging to explain the JWST observations without invoking exotic physics or revolutionary changes to established theory. The development of dark matter cosmology in the 1970s and 1980s, pioneered by researchers like Vera Rubin, Kent Ford, and Joel Primack, created the theoretical framework within which modern galaxy formation models operate. Rubin's observations of galaxy rotation curves revealed the existence of invisible matter that outweighs ordinary matter by factors of 5 or more. This discovery fundamentally changed our understanding of how galaxies form and evolve, but it also established the theoretical constraints that make rapid early galaxy formations so difficult to explain. The computer simulation revolution, led by researchers like Jim Peebles, Simon White, and Carlos Frenk, translated theoretical insights into detailed predictions about cosmic structure formation. The Millennium Simulation and its successors created the standard timeline of cosmic evolution against which the JWST observations are now being measured. These simulations successfully reproduced the large-scale structure of the modern universe, but they also made specific predictions about early galaxy properties that the JWST observations appear to violate. The development of the Hubble Space Telescope in the 1990s created the observational foundation upon which the current revolution builds. Hubble's deep field observations revealed the first glimpses of early galaxies, establishing the techniques and analytical methods that JWST has now extended to unprecedented depths. The surprise is not that JWST can see early galaxies. Hubble showed us they existed, but that these galaxies appear so different from what both Hubble observations and theoretical models predicted. The theoretical work on cosmic inflation by Alan Guth, Andre Linde, and others provided both the framework for understanding the universe's large-scale properties and the potential mechanisms that might explain rapid early evolution. Inflation theory explains the uniformity of the cosmic microwave background and the generation of density fluctuations that seed structure formation, but it also allows for exotic scenarios that might accelerate early cosmic evolution. The discovery of cosmic acceleration in 1998 by teams led by Saul Perlmutter, Brian Schmidt, and Adam Ries revealed that the universe contains a mysterious dark energy component that drives accelerating expansion. This discovery showed that the universe is stranger than we had imagined and opened the door to considering other exotic physics that might explain the JWST observations. Perhaps most importantly, the work of theorists like Jim Peebles, who spent decades developing the standard model of cosmology, created the intellectual framework that the JWST discoveries are now challenging. Peebles' work on galaxy formation, structure formation, and cosmological parameter estimation established the theoretical edifice that these new observations are forcing us to reconsider. The development of precision cosmology through projects like the Cosmic Background Explorer (COBE), the Wilkinson Microwave Anisotropy Probe (WMAP), and the Planck satellite created the observational constraints that any new theory must satisfy. These missions measured the properties of the cosmic microwave background with extraordinary precision, establishing tight limits on cosmological parameters and the timeline of cosmic evolution. The intellectual courage of these pioneering researchers is particularly relevant to the current crisis. Each generation of cosmologists had to be willing to challenge established ideas when confronted with new observations. Hubble overturned the static universe, Gamow challenged steady-state cosmology, and Rubin revealed the dominance of dark matter. Now a new generation of researchers must decide whether to defend established theory or embrace revolutionary change. Dr. Jim Peebles, whose work laid the foundation for modern cosmology, reflects on this intellectual inheritance. Science progresses by building on the work of previous generations, but also by being willing to abandon ideas when they no longer match observations. The JWST discoveries represent exactly the kind of challenge that drives science forward. They force us to question our assumptions and develop deeper understanding. The current crisis in cosmology is thus not a failure of previous research, but its ultimate success. The theoretical framework developed over the past century made specific, testable predictions about early galaxy formation. The fact that these predictions appear to be wrong doesn't invalidate the previous work. It validates the scientific method that produced theories capable of being tested and, when necessary, revised or replaced. Der Sit Ball, Testen Denning. The implications of the JWST discoveries extend far beyond galaxy formation, potentially requiring us to rewrite the entire story of cosmic evolution. If these mature galaxies truly existed when the universe was only 400 million years old, then virtually every aspect of the cosmic timeline, from the first moments after the Big Bang to the eventual fate of the universe, may need fundamental revision. The standard cosmological timeline tells a story of gradual, hierarchical development. In the first moments after the Big Bang, the universe was a hot, dense soup of elementary particles. As it expanded and cooled, these particles combined to form the first atomic nuclei during Big Bang nucleosynthesis, roughly 3 minutes after the initial singularity. For the next 380,000 years, the universe remained opaque to light as free electrons scattered photons before atoms could form. Recombination, when electrons first bound to protons to create neutral atoms, marked the dawn of the cosmic dark ages, a period lasting several hundred million years when no stars existed to illuminate the cosmos. The first stars were supposed to ignite around 200–400 million years after the Big Bang, ending the Dark Ages and beginning the epoch of reionization, as their intense radiation ionized the surrounding hydrogen gas. This carefully constructed timeline, confirmed by observations of the cosmic microwave background and computer simulations of structure formation, now faces a fundamental challenge. If massive, mature galaxies existed just 400 million years after the Big Bang, then star formation, galaxy assembly, and cosmic evolution must have proceeded at rates that challenge our understanding of physics itself. Dr. Abraham Loeb from Harvard, who has spent decades studying the first stars and galaxies, describes the magnitude of the revision required. We're not talking about minor adjustments to the cosmic timeline. We're potentially looking at a complete restructuring of how we understand the universe's youth. Everything from the end of the Dark Ages to the pace of chemical evolution may need to be reconsidered. The implications ripple backward through cosmic history. If galaxy formation proceeded so rapidly, then the first stars must have formed much earlier than expected, perhaps within just 100–200 million years after the Big Bang. This compressed timeline requires star formation has been far more efficient than any theoretical model predicts, potentially involving entirely new physical processes operating in the early universe. The chemical evolution timeline faces even more severe challenges. The heavy elements observed in these early galaxies, carbon, oxygen, nitrogen, and iron, can only be produced in stellar cores and distributed through supernova explosions. The abundance patterns suggest multiple generations of stellar evolution compressed into timeframes that seem physically impossible. Consider the implications for stellar nucleosynthesis, the process by which stars forge heavy elements in their cores. Massive stars that produce elements like oxygen and silicon through nuclear fusion require millions of years to complete their life cycles, even under the most extreme conditions. The presence of these elements in galaxies from the early universe suggests that several generations of such stars had already lived and died, requiring timescales that exceed the available cosmic time. The timeline revision also affects our understanding of supermassive black hole formation and growth. These early galaxies appear to harbor black holes with masses of millions to billions of solar masses, objects that should require hundreds of millions of years to grow from stellar remnants. If such massive black holes existed when the universe was only 400 million years old, either they formed through exotic mechanisms or they grew at rates that violate our understanding of accretion physics. The cosmic reionization timeline faces similar challenges. The epoch of reionization, one when the first stars and galaxies produced enough ultraviolet radiation to ionize hydrogen throughout the universe, is constrained by observations of distant quasars and the cosmic microwave background. If large populations of mature galaxies existed earlier than expected, reionization might have begun and proceeded differently than current models predict. Dr. Stephen Furlanetto from UCLA, an expert on cosmic reionization, explains the complexity. The timing and sources of reionization are intimately connected to when and how the first galaxies formed. If we need to revise the galaxy formation timeline so dramatically, it will require corresponding changes to our understanding of how the universe transitioned from darkness to light. The revised timeline might also affect our understanding of dark matter's role in early structure formation. The rapid assembly of massive galaxies suggests that dark matter halos, the gravitational scaffolding upon which galaxies form, must have assembled much more quickly than standard models predict. This might require modifications to our understanding of dark matter properties or the physics of structure formation in the early universe. The implications extend to the ultimate fate of the universe as well. The timeline of cosmic evolution is intimately connected to the balance between matter, radiation, and dark energy at different epochs. If the early universe was far more active than expected, it might indicate that the relative importance of these components evolved differently than we currently believe. Some researchers are exploring whether the fundamental forces of physics might have had different strengths in the early universe, allowing for accelerated evolution. If gravity was stronger, nuclear fusion more efficient, or electromagnetic interactions different in the past, It could explain the rapid development observed in these early galaxies, while maintaining consistency with observations from later cosmic epochs. The psychological impact of revising the cosmic timeline extends beyond technical astrophysics to our fundamental understanding of our place in the universe. The standard timeline provided a satisfying narrative of gradual development from simplicity to complexity, culminating in the emergence of life and intelligence after billions of years of cosmic evolution. The JWST discoveries suggest that the universe was capable of rapid, almost explosive development that challenges this narrative of patient cosmic construction. If massive, complex galaxies could form in just a few 100 million years, it implies that the universe has been capable of far more dramatic and rapid change than we previously imagined. Dr. Martin Rees from Cambridge University, whose work spans theoretical cosmology and astrobiology, reflects on the broader implications. These discoveries remind us that the universe is under no obligation to conform to our expectations or develop according to our timelines. The cosmos has apparently been full of surprises from its very beginning. The revision of cosmic timelines also affects our estimates of when life might have first emerged in the universe. If complex galaxies with heavy elements existed much earlier than expected, the cosmic environment suitable for planet formation and potentially life might have developed billions of years sooner than current models suggest. As we grapple with these timeline revisions, we're forced to confront the possibility that our understanding of cosmic evolution has been fundamentally incomplete. The universe may be far more dynamic, creative, and surprising than even our most sophisticated theories have suggested. The JWST discoveries don't exist in isolation. They're part of an interconnected web of physical understanding that spans from quantum mechanics to cosmology. When observations challenge fundamental assumptions about galaxy formation, the implications ripple through multiple branches of physics, potentially requiring revisions to theories that seemed well established, forcing physicists to reconsider basic principles about how the universe operates. At the most fundamental level, these discoveries challenge our understanding of time itself in the early universe. The physics of stellar evolution, nuclear fusion, and gravitational collapse operate according to well-defined timescales based on fundamental constants like the speed of light, the gravitational constant, and the strong nuclear force. If galaxies evolved much more rapidly than these timescales allow, it suggests either that our understanding of these processes is incomplete, or that the fundamental constants themselves might have been different in the early universe. The possibility of varying fundamental constants represents one of the most profound challenges to physics. Had these constants, the speed of light, Planck's constant, the elementary charge, are thought to be universal and unchanging. They determine everything from the rate of radioactive decay to the strength of chemical bonds. If they were different in the early universe, it would require a complete revision of our understanding of fundamental physics. Dr. John Barrow from Cambridge University, who pioneered theoretical work on varying constants, explains the implications. If fundamental constants change over cosmic time, it would affect every physical process from nuclear fusion in stellar cores to the formation of atoms themselves. The rapid evolution we're seeing might be a signature of a universe where physics operated differently when it was young. The discoveries also challenge our understanding of thermodynamics and statistical mechanics in extreme environments. Galaxy formation is fundamentally a process of gravitational collapse and gas cooling, governed by the laws of thermodynamics. The rapid formation of organized structures suggests either that thermodynamic processes operated far more efficiently in the early universe, or that unknown mechanisms accelerated the conversion of gravitational potential energy into organized motion. Stellar physics faces equally profound challenges. The nuclear fusion processes that power stars and create heavy elements operate according to well-understood quantum mechanical principles. The presence of heavy elements in early galaxies suggests that multiple generations of stars completed their entire life cycles in timeframes that seem to violate the known physics of stellar evolution. Dr. Ken Nomoto from the University of Tokyo, an expert on stellar nucleosynthesis, describes the challenge. The chemical abundance patterns we're seeing in these early galaxies require nuclear processes that operated much more rapidly than laboratory physics suggests is possible. Either stellar evolution was dramatically different in the early universe, or we're missing crucial physics in our understanding of how stars forge and distribute heavy elements. The field of particle physics also faces implications from these discoveries. If the early universe was far more active than expected, it might indicate the presence of exotic particles or forces that don't exist in the modern cosmos. Some theoretical models propose that additional particles or interactions might have existed in the high-energy environment of the early universe, potentially explaining the rapid structure formation. Dark matter physics represents another area where the JWST discoveries might require fundamental revisions. The rapid assembly of massive galaxies suggests that dark matter must have clumped together much more efficiently than standard models predict. This might require new understanding of dark matter's properties, its interactions with ordinary matter, or its behavior in the extreme conditions of the early universe. Dr. Lisa Randall from Harvard, whose work explores connections between particle physics and cosmology, notes, "These observations might be telling us something profound about dark matter that we've missed. Perhaps dark matter had different properties in the early universe, or perhaps it interacts with ordinary matter in ways we haven't yet discovered." The implications extend to our understanding of space-time itself. General relativity describes how matter and energy curve space-time, but these descriptions assume that the laws of physics remain constant across space and time. If galaxy formation proceeded much more rapidly than relativity allows, it might indicate that Einstein's equations require modification, or that space-time itself has properties we don't yet understand. String theory and other approaches to quantum gravity might offer insights into these puzzles. These theories predict that at extremely high energies, such as those present in the early universe, additional dimensions of space might become important, or entirely new physical phenomena might emerge. The rapid evolution observed in early galaxies might be a signature of physics operating in regimes where quantum gravity becomes important. The discoveries also challenge our understanding of information theory and entropy in cosmological contexts. The rapid formation of organized structures appears to violate the general principle that complex organization requires time to develop from simpler initial conditions. This might indicate that the early universe had access to information or organizational principles that we don't yet understand. Quantum field theory, which describes the behavior of particles and forces, might also require revision. The standard model of particle physics makes specific predictions about how particles behave at high energies and densities. If these predictions are inadequate to explain rapid early galaxy formation, it might indicate the existence of new particles, forces, or quantum phenomena. Perhaps most fundamentally, these discoveries force physicists to confront the limits of reductionism, the assumption that complex phenomena can be understood by studying their component parts. Galaxy formation involves the collective behavior of trillions of particles over cosmic timescales, and the emergence of organized structures might involve principles that can't be reduced to the behavior of individual particles. As physics grapples with these implications, we may be witnessing the emergence of entirely new fields of study that bridge cosmology, particle physics, and information theory in unprecedented ways. Far from providing answers, the JWST discoveries have opened a Pandora's box of new questions that push the boundaries of human knowledge into uncharted territory. Each explanation for these impossibly mature early galaxies raises additional mysteries that challenge our understanding not just of cosmology, but of the fundamental nature of reality itself. If primordial black holes seeded early galaxy formation, where did they come from? The conditions required to form massive black holes directly from the collapse of primordial gas clouds are so extreme that they challenge our understanding of the early universe's density structure. What mechanism could have created the enormous density fluctuations needed for direct collapse? And if such mechanisms existed, why don't we see evidence for them in the cosmic microwave background? The chemical evolution puzzle raises equally perplexing questions. If multiple generations of stars lived and died in just a few 100 million years, what drove such rapid stellar evolution? Could there have been exotic stellar formation mechanisms that no longer operate in the modern universe. Perhaps most intriguingly, could the early universe have experienced phases of stellar evolution that we've never imagined, periods when stars formed, lived, and died according to physical processes we don't yet understand? Dr. Volker Brom from UT Austin, who has spent decades modeling the first stars, articulates the mystery. We're confronting the possibility that stellar physics in the early universe was fundamentally different from what we observe today. Maybe the first stars weren't just bigger or brighter than modern stars. Maybe they evolved according to entirely different rules. The dark matter conundrum deepens with these discoveries. If dark matter enabled such rapid structure formation in the early universe, why did this process apparently slow down dramatically in later cosmic epochs? What changed about dark matter's behavior or properties that caused galaxy formation to become the slow, gradual process we observe in more recent times? Was is ooit teersbrek? Souli teersbrekte, what a beersbrekte. Some researchers are exploring whether dark matter might have undergone phase transitions similar to those that affected ordinary matter in the early universe. Just as ordinary matter transitioned from a plasma to neutral atoms during recombination, dark matter might have experienced its own transitions that temporarily enhanced its ability to clump into structures. The cosmic inflation mystery takes on new dimensions in light of these discoveries. Standard inflation theory predicts that quantum fluctuations should have been stretched to cosmic scales, creating the density variations that seed structure formation. But the rapid galaxy formation observed by JWST might require initial fluctuations far larger than inflation models predict. This cosmic inflation dendostrafika. Does this mean inflation worked differently than we thought, or that additional mechanisms operated alongside inflation to create the conditions for rapid structure formation? Dr. Alan Guth from MIT, who originally proposed cosmic inflation, acknowledges the puzzle. These observations might be telling us that the early universe was even stranger than inflation theory predicts. Perhaps multiple mechanisms were operating simultaneously to create the conditions we're observing. The question of cosmic fine-tuning becomes even more mysterious. The rapid formation of complex galaxies in the early universe suggests that the conditions for structure formation were not just adequate, but optimal in ways we don't yet understand. This raises profound questions about why the universe seems so perfectly suited for rapid development of complexity. Perhaps most fundamentally, these discoveries raise questions about the nature of time and causality in cosmic evolution. If galaxies could assemble so rapidly, what does this tell us about the relationship between physical processes and the flow of time? Could there be aspects of temporal evolution in the early universe that we've completely missed? The anthropic principle takes on new significance in light of these discoveries. If the universe was capable of such rapid evolution in its youth, what does this mean for the emergence of life and intelligence? Could complex chemistry and potentially life have emerged much earlier in cosmic history than we previously thought possible? The multiverse hypothesis becomes both more appealing and more mysterious. If our universe is just one of countless others with varying properties, what determines which universes develop rapidly and which evolve slowly? Is there some deeper principle that governs the distribution of cosmic properties across the multiverse? Dr. Max Tegmark from MIT poses the ultimate question: are we glimpsing the tip of an iceberg of cosmic mysteries that we've barely begun to explore? These discoveries might be showing us that the universe is far stranger, more dynamic, and more wonderful than we ever imagined. The JWST discoveries have transformed cosmology from a field focused on confirming established models to one confronting fundamental mysteries about the nature of cosmic evolution. Rather than closing chapters in our understanding, these observations have opened entirely new volumes of cosmic mystery. The JWST discoveries represent just the beginning of a new era in observational cosmology. As revolutionary as these findings are, they're based on only the first few months of data from humanity's most powerful space telescope. The coming decade promises observations that will either confirm the radical implications of these early results or reveal even more surprising aspects of cosmic evolution that we haven't yet imagined. JWST itself has barely scratched the surface of its observational potential. The telescope's 20-year mission timeline means we're only about 10% through its planned operational life. Future deep-field surveys will probe even further into cosmic time, potentially revealing galaxies from when the universe was just 300 million years old. These observations will test whether rapid galaxy formation was universal in the early universe or limited to special regions or conditions. The upcoming JWST, Advanced Deep Extragalactic Survey. Deep Field will spend over 700 hours staring at a single patch of sky, creating the deepest image of the universe ever obtained. This observation will reach galaxies so distant and faint that their light has been traveling toward us for over 13.5 billion years, essentially to the edge of the observable universe. Dr. Daniel Eisenstein from Harvard, who leads the JD survey, describes the ambitious scope. We're planning observations that will make Hubble's deep fields look like snapshots. We'll be able to study not just individual galaxies from the early universe, but entire populations of them, understanding how common these rapidly evolved systems really are. Ground-based telescopes are also entering a revolutionary phase. The extremely large telescope ELC, currently under construction in Chile, will have a primary mirror 39 meters in diameter, nearly 4 times larger than any existing ground-based telescope. When combined with adaptive optics systems that correct for atmospheric turbulence, the ELT will achieve resolution and sensitivity that complement JWST's capabilities. Undersökungen beleuchten som får hålldentillusion. With the Corbier dander Shirati. The ELT's massive collecting area will enable spectroscopic studies of early galaxies with unprecedented detail. While JWST can detect these distant objects and measure their basic properties, the ELT will be able to map their internal structure, measure the velocities of gas and stars within them, and determine how these early galaxies acquired their material through mergers and accretion. Space-based observatories planned for the 2030s push even further into uncharted territory. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct the largest survey of the universe ever attempted, potentially discovering millions of early galaxies. Its wide field of view will reveal whether the rapidly evolved galaxies found by JWST are rare exceptions or common features of the early universe. The proposed Habitable Worlds Observatory, tentatively planned for the 2040s, will combine unprecedented imaging capabilities with advanced spectroscopic instruments. This telescope will be able to study the atmospheric compositions of planets around early stars, potentially determining whether the rapid chemical evolution observed in early galaxies enabled planet formation and possibly life much earlier in cosmic history than previously thought. Gravitational wave astronomy represents another frontier that will provide crucial insights into early cosmic evolution. The planned Laser Interferometer Space Antenna, LISA, scheduled for launch in the 2030s, will be sensitive to gravitational waves from the merger of supermassive black holes in the early universe. These observations will provide direct evidence for or against scenarios where primordial black holes seeded early galaxy formation. Dr. Monica Kolpe, from the University of Milan-Bicocca, who works on laser science, explains the potential laser will let us hear the early universe in ways we've never been able to before. If supermassive black holes were merging and growing rapidly in early galaxies, we should be able to detect the gravitational wave signals from these ancient events. Radio astronomy is experiencing its own revolution with facilities like the Square Kilometre Array, SKA, which will be the world's largest radio telescope when completed in the late 2020s. The SKA will be able to map the distribution of neutral hydrogen throughout the early universe, providing a three-dimensional picture of how matter was distributed when the first galaxies formed. These radio observations will be crucial for understanding the cosmic environment in which rapid galaxy formation occurred. If early galaxies formed in regions of unusually high gas density, or if there were large-scale flows of matter that accelerated structure formation, the SKA should be able to detect these phenomena. Advanced computer simulations will also play crucial roles in interpreting future observations. The next generation of cosmological simulations will incorporate the physics of primordial black holes, exotic dark matter interactions, and modified gravity theories, allowing researchers to test which theoretical scenarios can reproduce both the JWST observations and all other cosmological data. Machine learning and artificial intelligence are already revolutionizing how astronomers analyze complex datasets. Future AI systems will be able to identify patterns in observational data that human researchers might miss, potentially revealing new classes of early galaxies or unexpected correlations that provide clues to the physics of rapid cosmic evolution. Perhaps most excitingly, entirely new types of observations may become possible as technology advances. Proposed concepts include interferometers in space that could directly image the surfaces of stars in nearby galaxies, neutrino telescopes sensitive enough to detect signals from early stellar nucleosynthesis, and quantum sensors that could reveal previously undetectable aspects of space-time curvature. The convergence of these multiple observational approaches promises to either resolve the current crisis in cosmology or reveal that the universe is even stranger than the JWST discoveries suggest. The JWST discoveries have ignited what may become the most significant theoretical debate in cosmology since the development of the Big Bang model itself. Across universities and research institutes worldwide, theorists are working frantically to develop new frameworks that can explain these impossible early galaxies while maintaining consistency with decades of other cosmological observations. The result is an emerging battle of ideas that will likely define the next decade of theoretical physics. The conservative camp, led by researchers who helped develop the standard lambda CDM model, argues for caution and incremental modifications rather than revolutionary change. These scientists propose that improvements to existing models, better treatment of stellar feedback, more sophisticated descriptions of gas cooling, or refined understanding of dark matter clustering might explain the observations without abandoning well-tested theoretical frameworks. Dr. Carlos Frank from Durham University, whose work on dark matter simulations helped establish the standard model, represents this perspective. Before we throw out decades of successful theory, we need to exhaust all possibilities for explaining these observations within existing frameworks. And with Dr. Carlos Frank from Durham University, whose work on dark matter simulations helped establish the standard model, history teaches us that apparent revolutionary discoveries sometimes have more mundane explanations. The conservative approach focuses on identifying overlooked physical processes that might accelerate early galaxy formation. Perhaps magnetic fields were stronger in the early universe, enhancing star formation efficiency. Maybe the initial mass function of stars was different, allowing for more rapid chemical evolution, or possibly the efficiency of gas cooling in primordial environments was higher than current models assume. The radical camp, meanwhile, embraces the JWST observations as evidence for fundamental physics beyond the standard model. These researchers are developing theories involving modified gravity, exotic dark matter, varying fundamental constants, or entirely new fields and forces that operated in the early universe. Dr. Stacy McGaw from Case Western Reserve University advocates for this revolutionary approach. When observations consistently contradict theoretical predictions, it's time to question the theory, not dismiss the observations. The universe is telling us something profound about physics that we've been missing. The theoretical battle extends beyond just cosmology to fundamental physics itself. String theorists are exploring whether extra dimensions or exotic string states might explain rapid early galaxy formation. Quantum gravity researchers are investigating whether space-time itself might have different properties in the extreme conditions of the early universe. Some theorists are developing hybrid models that combine elements from both conservative and radical approaches. These theories might invoke modifications to general relativity that become important only in the early universe, or dark matter particles, with interactions that change as the universe evolves. The debate has created unusual alliances and bitter divisions within the scientific community. researchers who have collaborated for decades find themselves on opposite sides of fundamental questions about the nature of cosmic evolution. Graduate students must choose between advisors representing different theoretical camps, knowing that their career prospects may depend on which approach ultimately proves correct. International conferences have become intellectual battlegrounds where different theoretical camps present their latest models and challenge their competitors' assumptions. The normally collegial atmosphere of academic meetings has given way to intense debates that sometimes border on personal conflicts. Funding agencies find themselves in the difficult position of deciding which theoretical approaches deserve support. Should they fund conservative research that builds incrementally on established models, or radical projects that might revolutionize our understanding, but could also prove to be dead ends? The European Southern Observatory and NASA have commissioned special theoretical working groups to evaluate the implications of the JWST discoveries and recommend research priorities. These groups include representatives from different theoretical camps, but reaching consensus has proven challenging when fundamental assumptions about cosmic evolution remain in dispute. The European Southern Observatory and NASA have commissioned special theoretes betrothed. Journal editors face similar challenges in evaluating papers that propose radical revisions to established theory. The peer review process becomes particularly complex when reviewing claims that challenge the very foundations of the field. How do you evaluate a paper that proposes modifications to general relativity or exotic dark matter interactions? The theoretical battle is being fought not just in academic journals, but in the public sphere. Popular science books and documentaries present competing visions of cosmic evolution, and social media platforms buzz with debates about which theoretical approach is most likely to succeed. Perhaps most significantly, the theory wars are driving rapid innovation in theoretical physics. The urgency of explaining the JWST observations has catalyzed new mathematical techniques, computational methods, and conceptual frameworks that might not have developed otherwise. Dr. Max Tegmark from MIT captures the excitement and uncertainty of the moment. We're living through one of those rare periods in science when fundamental assumptions are being questioned and new theoretical frameworks are being born. It's intellectually exhilarating and scientifically terrifying at the same time. The resolution of these theory wars will likely take years or even decades, but the outcome will fundamentally shape our understanding of the universe and our place within it. We are living through a scientific revolution, and most of us don't even realize it. The JWST discoveries aren't just challenging specific models or theories, they're potentially overthrowing the entire conceptual framework within which we understand cosmic evolution. This is what it feels like to be alive during one of those rare moments when human understanding takes a quantum leap forward, leaving old certainties behind and opening vast new territories of knowledge. Historical scientific revolutions share common characteristics that we can recognize in our current moment. They begin with anomalous observations that don't fit existing theories. Initially, scientists try to explain these anomalies within established frameworks, proposing modifications or refinements that preserve the core theoretical structure. But as the anomalies persist and multiply, a growing number of researchers begin to question fundamental assumptions. The JWST discoveries fit this pattern perfectly. The initial response was to question the observations themselves, perhaps systematic errors, calibration problems, or misinterpretation of complex data. When these explanations proved inadequate, scientists attempted to modify existing models of galaxy formation to accommodate the unexpected findings. Now, as evidence accumulates that these modifications are insufficient, we're entering the revolutionary phase where fundamental assumptions are being challenged. Dr. Thomas Kuhn, whose work on scientific revolutions remains influential decades after its publication, described this process as a paradigm shift, a fundamental change in the basic assumptions, concepts, and practices that define a scientific discipline. The JWST discoveries appear to be triggering exactly such a shift in cosmology. What makes this revolution particularly fascinating is that we can observe it unfolding in real time. Social media platforms, preprint servers, and online conferences allow us to watch the scientific process as it happens. We can see initial skepticism giving way to grudging acceptance, watch theoretical camps form and clash, and observe the emergence of new ideas that might eventually replace established theories. The psychological dimension of scientific revolution is often overlooked, but it's crucial for understanding how science actually progresses. Researchers who have built careers on theories now under challenge face difficult choices. Do they defend their life's work against revolutionary claims, or do they embrace the possibility that their fundamental assumptions might be wrong? Dr. Sandra Faber from UC Santa Cruz, whose work on galaxy evolution spans 4 decades, describes the emotional complexity. It's intellectually exciting to see the field potentially on the verge of breakthrough discoveries, but it's also unsettling to realize that theories you've spent your career developing might need fundamental revision. Science demands intellectual honesty, even when it's personally uncomfortable. The generational aspect of scientific revolution is particularly evident in the current crisis. Younger researchers, who haven't invested decades in developing the theories now under challenge, seem more willing to embrace radical explanations for the JWST observations. Senior scientists, while intellectually committed to following evidence wherever it leads, sometimes show more resistance to revolutionary interpretations. This generational dynamic creates opportunities for rapid advancement among younger researchers willing to explore radical possibilities. Graduate students and postdocs who develop successful new theoretical frameworks could find themselves at the forefront of a transformed field, while more established researchers might struggle to adapt to rapidly changing conceptual landscapes. The international dimension of modern astronomy adds complexity to the revolutionary process. Different scientific cultures approach anomalous data with varying degrees of skepticism and openness to radical change. European researchers, working within traditions that emphasize theoretical rigor, sometimes clash with American colleagues who place greater emphasis on observational discoveries. Asian astronomers bring different philosophical perspectives to questions about the nature of cosmic evolution. The rapid pace of modern communication accelerates the revolutionary process in ways that weren't possible during previous scientific upheavals. When Einstein developed relativity theory, it took years for his ideas to spread through the global scientific community. Today, theoretical papers proposing radical revisions to cosmology can be downloaded and debated within hours of their publication. This acceleration has both positive and negative consequences. It allows for rapid testing and refinement of new ideas, but it also creates pressure for premature conclusions and sensationalized interpretations. The 24-hour news cycle demands immediate answers to questions that might require years of careful research to resolve properly. The public dimension of the current revolution is unprecedented in scientific history. Previous paradigm shifts occurred largely within scientific communities, with public awareness developing only gradually as new theories became established. The JWST discoveries, by contrast, have generated immediate public interest and media coverage that influences how the scientific community itself responds to the observations. Social media platforms buzz with discussions about whether the Big Bang theory is wrong, while popular science communicators struggle to explain complex cosmological concepts to audiences hungry for revolutionary discoveries. This public engagement creates both opportunities and pressures that didn't exist during previous scientific revolutions. The interdisciplinary nature of the current crisis extends the revolutionary implications beyond just cosmology. If our understanding of cosmic evolution requires fundamental revision, it could affect fields ranging from particle physics to astrobiology. The search for life beyond Earth, for example, might need to consider that habitable conditions could have emerged much earlier in cosmic history than previously thought. Perhaps most significantly, we're experiencing a revolution in how scientific revolutions themselves unfold. The traditional model of paradigm shifts, developed by studying historical cases, assumed that revolutionary changes occurred primarily through the replacement of older generations of scientists by younger ones committed to new paradigms. But modern scientific institutions, international collaborations, and rapid communication might allow for more dynamic and rapid transitions between theoretical frameworks. Dr. Lee Smolin, from the Perimeter Institute for Theoretical Physics, reflects on the broader implications. We're not just witnessing a potential revolution in cosmology, we're seeing how scientific revolutions happen in the age of global communication, international collaboration, and public engagement. The process itself is evolving. The outcome of this revolution remains uncertain. The JWST observations might ultimately be explained within modified versions of existing theories, or they might require entirely new theoretical frameworks that overturn our understanding of cosmic evolution. What seems certain is that cosmology will emerge from this period fundamentally changed, with new concepts, new questions, and new ways of understanding our place in the universe. As we live through this remarkable moment, we have the rare privilege of witnessing human knowledge expand in real time. The universe has presented us with a puzzle that challenges our deepest assumptions about cosmic evolution, and the solution, whatever it proves to be, will likely transform our understanding of reality itself. The impossible galaxies discovered by the James Webb Space Telescope have shattered our comfortable assumptions about cosmic evolution. We thought we understood how the universe grew from simplicity to complexity. We believed we had mapped the timeline of stellar birth, galactic assembly, and chemical enrichment. We were confident in our models, our mathematics, our theories. We were wrong. These ancient giants, blazing across the cosmic dark just 400 million years after the Big Bang, force us to confront a humbling truth. The universe has been far stranger, far more dynamic, and far more creative than we ever imagined. The crisis in cosmology isn't a failure of science. It's science working exactly as it should. When observations challenge theory, when reality refuses to conform to our expectations, we don't retreat into comfortable assumptions. We follow the evidence, however uncomfortable, wherever it leads. Perhaps gravity behaved differently in the universe's youth. Perhaps dark matter had exotic properties we've never considered. Perhaps the fundamental constants that govern physics itself evolved as the cosmos matured. Or perhaps primordial black holes seeded rapid galaxy formation in ways our models never anticipated. The answers remain tantalizingly out of reach, but the questions themselves have transformed our field. We stand at the threshold of what could be the most significant revision to our understanding of cosmic evolution since Einstein first proposed that space-time could curve. These discoveries remind us that science is not a collection of established facts, but an ongoing conversation between human curiosity and cosmic mystery. The universe has just spoken, challenging our most fundamental assumptions about how everything began. Our response will define the next chapter in humanity's quest to understand our cosmic origins. In the end, these impossible galaxies teach us something profound about the nature of discovery itself. The universe is under no obligation to conform to our theories. No matter how elegant or well-tested they might be, reality remains the ultimate arbiter of truth, and reality has just delivered a verdict that will reshape cosmology for generations to come. What aspect of these discoveries fascinates you most? The possibility that our understanding of time and physics in the early universe is fundamentally incomplete, or the prospect that we might be living through one of the greatest scientific revolutions in history? What aspect of these discoveries fascinates you most? What aspect of these discoveries fascinates you most? Thank you for joining me on this journey to the edge of cosmic understanding. If this exploration of impossible galaxies and revolutionary discoveries sparked your curiosity about the mysteries that still surround us, I'd be grateful if you'd like this video and subscribe to join our community of cosmic explorers. The universe has just shown us that it's far stranger and more wonderful than we ever imagined, and this is only the beginning. Our cosmic story continues to unfold, with each new discovery, each impossible observation, each moment when reality challenges our deepest assumptions. Click here to explore more cosmic mysteries that are reshaping our understanding of the universe, or dive into our complete collection of space documentaries that reveal the ongoing revolution in our cosmic perspective.